হ্যালো, হ্যাঁ আপনি লাইভ স্ট্রিম শুরু করে দিয়েছেন? ওকে, লাইভ স্ট্রিম শুরু করে দিয়েছেন, ঠিক আছে। আর আপনাকে মমিতা ম্যাম আপনাকে ফোন করছে, আপনি একটু কথা বলেন, ঠিক আছে? ওকে, প্লিজ কল নাও।
He seems engaged. I'm not being able to call him.
Yeah, but I told him that he will call him. So please try once again, because he started the live stream.
It's okay, I'm calling. So, Dr. Purba, so if Professor Raichaudhuri is here and Dean sir agrees, so I think we can start now. It's almost 10:05.
Yes. So, sir, shall we start now?
Yes, we can start.
Okay, thank you, sir. Respected Professor Jitendra Kumar Pandey, Dean of School of Basic and Applied Sciences of Adamas University, our honorable invited speaker, eminent Professor Amitava Raichaudhuri, Dr. Momita De, Head of the Physics Department at Adamas University, Professor Bimal Kumar Sarkar, Convener, NCFMP 2021, and other participants of this virtual meeting. Good morning, everyone. As you are all aware, we have assembled here on the occasion of National Conference on Frontiers in Modern Physics 2021, being organized by Physics Department from School of Basic and Applied Sciences at Adamas University. It is a continuous series of conference, and this is the third year of NCFMP. On behalf of the organizing committee of NCFMP, I welcome you all in this morning session of the second day of this conference. Also, let me take this opportunity on behalf of the NCFMP and personally to wish you all a very warm greeting. It was our great honor that yesterday we had with us Padma Bhushan, Padma Shri, Professor Vikas Sinha, Professor Sandip Kumar Chakraborty, Professor Saurabh Basu, and Professor Chittaranjan Sinha. We got an overwhelming response from all the contributor speakers and the other participants. And today, also in the pre-lunch session, we have three very eminent invited speakers, Professor Amitabh Rai Choudhury, Professor Arup Kumar Rai Choudhury, and Professor Bornali Ghosh. This will be followed by the invited lecture from Honorable Professor Devnarayan Jana in the post-lunch session. We are really grateful to have such renowned physicists among us, and we are eagerly waiting to hear from them. Let me end my address with deep thanks to all concerned, the authorities of the university, head of the Department of Physics, and different staff members, my fellow colleagues in the physics department for their guidance, support, and effort to make this program a success. Let me begin the first session, where we will listen to Professor Amitabh Rai Choudhury, who will talk about neutrino novelties. I will request the audience, if you have any question to Professor Amitabh Rai Choudhury after his talk, please write it down in the chat box and we will take one or two questions to him. Now, may I request Professor Jitendra Kumar Pandey to act as the session chair. Professor Pandey, who did his PhD from National Chemical Laboratory, Pune, having over 20 years of research and teaching experience in national and international institutions. His research areas are in the bio-nanocomposites, degradation and stabilization of polymer composite, nanomaterial for water treatment, synthesis, characterization, and analysis of any forced composites. He has published more than 100 research articles, 17 patents, 5 books, and successfully completed various research projects from the Department of Science and Technology, Government of India. Professor Pandey is a member of the National Academy of Sciences, India. He is a recipient of Brain Pool Fellowship from Government of South Korea, Max Planck Fellowship from Germany, and Fellowship from Japan Society of Promotion of Sciences, Japan. Professor Pandey, can you please take over from here, sir?
Thank you, Purva. Good morning, everyone. Good morning, Rai Choudhury, sir. We are blessed by having you, and we all know that you are one of our well-wishers for the School of Basic and Applied Science in Adamas University. This is always a pleasure and honor to introduce you for our events, and I am sure we all know that it is difficult to introduce Professor Rai Choudhury in just 5 minutes, 2 minutes, or 7 minutes. He himself is an institution. He has been looking after so many things. He has been an institutional builder. He has been a mentor, great teacher, an outstanding researcher. But for those who joined newly or who may not be aware, I'll just go through very briefly. Currently, he is Professor Emeritus in University of Calcutta. He was educated at Presidency College, Kolkata, and Delhi University, obtained his PhD in particle physics from the University of Maryland, USA. And remember, it was old days, going US and receiving degree. It's not like the current situation. He was working with very renowned Professor Greenberg. He has held faculty position at the University of Kolkata for more than 30 years and was the Sri Tarak Nath Palit Professor of Physics during 1998 to 2017. And this professorship of Sir Tarak Nath Palit, it's very prestigious. People who know physics, they know how important and how difficult, how prestigious having this professorship. From 2005 to 2011, he was the director of Harish Chandra Research Institute, Allahabad, under the Department of Atomic Energy, India. He has done a lot of changes there. His his changes or his his plans and policies, people still remember at that place. He has had visiting appointment at various universities, including University of Oxford and Cambridge in the UK, at the University of California and Berkeley, and CERN in Geneva. Professor Rai Chaudhry's research contribution span many areas of particle physics, including the Higgs boson and neutrino mass models. He is recipient of several honors and distinctions, among which are the Shanti Swarup Bhatnagar Award and International Alumnus of the Year 2005. And International Alumnus of 2005. And in general, this is both Bhatnagar and having alumnus is extremely prestigious thing, and it's a great honor. It's kind of lifetime achievement. And I'm glad that in India also we respect the hardworking people, the researcher and teachers like Professor Rai Chaudhry. He is a fellow of the 3 National Science Academies of India, and all 3 are great academies. I don't think after these academy there is any academy remaining for fellowship. So, sir, this was very brief. I might have done some mistake. I might have missed some names, but believe me and trust me, in Department of Physics, in School of Basic and Applied Science, we always feel honored and always feel delighted to have you on board. And we all are eagerly waiting. Once campuses are fully open, we will invite you here. We want to meet you face to face. We want you to interact with our students of graduate and postgraduate. So, sir, thank you so much. And I am honored. Whole department is honored to have you, sir. Purva, over to you.
Thank you very much, Professor Pandey. You said many kind words about me, and I'm not sure I deserve all of them. It's my pleasure and my privilege to be addressing this august audience at the Adamas University. Let me tell you right away that I have pitched this talk at a rather introductory level. One could get into technicalities, but I thought that since this is a somewhat mixed audience, I would leave
perfectly
it.
Perfectly fine, sir. Yeah.
Okay, very good. So let me now begin my presentation. First, I will switch off my video, and then I'll begin the presentation. Is my screen shared?
Yes, sir. It's perfectly visible.
Very good, very good. So the topic of today's lecture in the National Conference on Frontiers in Modern Physics, the topic today is, this morning, is neutrino novelties. So first we have to recall for ourselves the way the neutrino was introduced into physics. It was introduced by Wolfgang Pauli in the 1930s, and the reason behind the proposal of the neutrino is the beta radioactive decay. If we compare the alpha decay and the beta decay, in an alpha decay, there's a parent nucleus which goes into a daughter nucleus emitting an alpha particle, and the energy of the alpha particle is determined very simply as the difference in the masses of the parent nucleus and the daughter nucleus. So whatever is not there, the difference in masses, and of course I use the units in which the velocity of light is 1. So I interchangeably use the terms mass and energy according to Einstein's relationship E equals mc squared. So therefore, the energy of the alpha particle is simply the difference in the parent and daughter nuclei masses. Now, in the case of beta decay, the observed decay products are the daughter nucleus and an electron. And one would have expected, in line with alpha decay, the electron to have a unique energy, being the difference in the masses of the parent and the daughter nucleus. However, it is found that the electron has an energy distribution, so the conservation of energy is brought into question, and Pauli answered this by introducing another particle, the neutrino, in this case, the anti-neutrino, which carries off the balance of the energy, and so therefore the energy remains conserved. Our focus will be on neutrinos and on anti-neutrinos. So just to put this in perspective, so here in this diagram, we have the energy being plotted in the x-axis, and in the y-axis, we have the number of electrons. Then the expected energy distribution in the absence of the neutrino would have been a line, a unique energy for the electron, but instead this distribution is seen, and that led Pauli to propose the neutrino. Now, the neutrino was not being seen, and therefore it had to be very difficult to observe. It was very light, and then it's uncharged, no electric charge, and it hardly interacts. These are the properties of the neutrino. It is produced in beta decay and in other reactions. For example, the decay of the pi meson, the charged pion, it decays. For example, the pi plus decays into a mu plus and a muon type neutrino. We will come to the distinction between the electron neutrino and the muon neutrino in a moment. But let's go on and also recall that neutrinos interact so little that they pass from one end of the earth to another without any interaction whatsoever most of the time. And for this reason, they're also harmless at any moment. Billions of neutrinos are going through our body without doing any damage because they don't interact. They interact very little. So for the same reason, it also is extremely difficult to detect a neutrino. So experiments to detect the neutrino and to find its properties are all very difficult. And much of the properties we know only in the last few years. And at this time, we know that there are three different kinds of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. They are associated with three charged leptons: the electron and its partners, its cousins, the muon and the tau. These are charged leptons, and there are neutrinos associated with each of the charged leptons. So these are the charged leptons, and these are the neutrinos. The neutrinos have no electric charge, and the charged leptons have charge -e. Now, when a neutrino interacts with a weak interaction, it produces the corresponding lepton. So an electron neutrino would produce an electron, a muon neutrino would produce a muon, and a tau neutrino would produce a tau lepton. Now, the neutrinos have two kinds of interactions. This is one kind of interaction, the charge changing interaction, where the neutrino becomes an electron, or a muon neutrino becomes a muon. And there's also another kind of reaction, which is called the neutral current interaction, in which the charge does not change and the neutrino remains a neutrino. Now, as we know, these are the quarks. These are the fundamental particles that we know. The top two rows and the three columns are the three kinds of quarks, the three generations of quarks. And then we have the leptons, about which we have mentioned. And our focus today will be on the third row, the neutrinos. The fourth column these are actually bosons. While these were all fermions, the quarks and leptons are fermions, these are bosons. And the bosons are the force carriers. They mediate the force. And the ones on which we will mainly be interested today are the Z boson and the W boson. These are responsible for the weak interactions. The W boson is responsible for the charge changing weak interaction, and the Z boson is responsible for the charge neutral weak interaction. We come to all of this in a moment, but before that, I should also include the Higgs boson in this picture, because the Higgs boson is responsible for the masses of the quarks, leptons, and the Z and the W. So now, how does the mass of mass emerge? The mass emerges from the Higgs mechanism, and the standard model describes the strong and electroweak interactions. It is mediated by, the forces are mediated by gluons for the strong interaction, the W and the Z boson for the weak interactions, and the photon for electromagnetism. Now, for fermions, there are two kinds, the left-handed fermion, and the right-handed fermion. Why do we classify the fermions into these categories? We do that because fermions carry two vectors with them. One vector is, of course, the momentum vector, and the other vector is the spin vector. And if we take the quantization direction of spin to be along the momentum, then the spin vector can be either along the momentum or anti-parallel to the momentum. And these two cases we distinguish by calling them left-handed and right-handed. Now it turns out that for a fermion to be massive, one requires both the left and the right-handed components of that fermion. So we have left and right-handed quarks, left and right-handed charged leptons, but only a left-handed neutrino in the standard model. In the standard model, there is no right-handed neutrino. For this reason, parity is violated, because parity would take left to right. And since there is no right-handed neutrino, parity is broken in the weak interactions. Also, because there is no right-handed neutrino, the neutrino is massless. So the mass term involves both the left and right. And in this case, there is no right-handed neutrino. So neutrinos are massless in the standard model. Now, of course, people who introduced the standard model had chosen the right-handed neutrino to be absent, because at that time it was believed that neutrinos are indeed massless in nature. But now we know that that is not true, and we'll come to that very, very soon. So as I was saying, there are two kinds of weak interactions, one mediated by the W, where an electron neutrino changes to an electron, and a neutron goes into a proton. This is a charge changing reaction. The neutron becomes a proton, which involves a change of charge, and a neutrino becomes an electron. There is the other kind of interaction, the neutral current interaction, which involves the exchange of the Z boson. And here are the Feynman diagrams for these processes. And the Z boson interaction has the feature that it doesn't change the initial and final particles. And if it's an electron neutrino to start with, it remains an electron neutrino. If it's a muon neutrino to start with, it remains a muon neutrino at the end. So therefore, the Z boson interactions are of the same strength for the electron type neutrino, the muon type neutrino, and the tau type neutrino. And further, they couple to all of them with the same strength. So this will be a property which we'll require later. So please keep this in mind, that the neutral interaction Z boson exchange is of the same strength and exists for all types of neutrinos. Now, neutrinos are very hard to detect, and so here is a cartoon where there's the senior professor who, because he's senior, he gets a seat, and then there's this junior faculty who is here. And have I lost my connection? Hello?
No, sir, it's absolutely audible and perfectly okay.
Okay, very good. And here's this junior member who is here, who is asked by this senior professor, "Did you see it?" And then he says, "No, nothing. I didn't see anything." And then the senior professor says, "Oh, then it was a neutrino." So if you don't see anything, then it means the neutrino, because the neutrino is identified by its absence. Okay, so how do we know now that neutrinos are massive? We know it through the solar neutrinos and the atmospheric neutrinos. I focus here on the solar neutrinos. So in the sun, what happens is 4 protons fuse together in a fusion reaction to produce a helium nucleus and 2 electrons and 2 neutrinos. So this is an exothermic process. It produces these final products and 27 MeV of energy. So this energy is what we see as sunlight, and the heat and light which we get from the sun is due to this 27 MeV of energy per reaction. And at the same time, the neutrinos which come from the sun are also reaching the Earth. Now, the number of neutrinos and their energy distribution can be calculated once we know the structure of the sun. How is its energy, how is its density distribution, what reactions are taking place, at what temperature, and so on. And using that, there are specialists, astrophysicists, who are experts in these calculations. They can make very robust prediction of the number of solar neutrinos reaching the Earth as a function of energy. So here, for example, I have plotted the energy in the x-axis, and in the y-axis, I have plotted the flux of neutrinos. Now, in the sun, several reactions are taking place, which together effectively give this one reaction. Now, each of these reactions has a neutrino flux of a typical energy. And so here I show the distribution of neutrinos, number of neutrinos as a function of the energy from different reactions. For example, the PP reaction, which is the most common, produces a lot of neutrinos. This is a logarithmic scale. So the number of PP neutrinos are very large, but they are of very low energy. Whereas the boron neutrinos, which go like this, they are of much higher energy, but of course, much less in number because it's a logarithmic scale. So therefore, they are much less in number than PP neutrinos. Higher energy neutrinos are easier to detect, and but the number of higher energy neutrinos is less. So experiments were mounted to look for the solar neutrinos, and they found the solar neutrinos. They detected neutrinos coming from the direction of the sun. However, there was a problem. What was the problem? The problem was that the number of neutrinos seen was less than the number of neutrinos predicted. The person who started this experiment, the first experiment, is Ray Davis Jr., who you see here pictured. And what he did was he put in a huge detector containing chlorine, in fact, carbon tetrachloride. And neutrinos hitting carbon tetrachloride produced the chlorine, from the chlorine atom, it would produce an argon atom in an excited state and an electron. What Davis could do was he noted that argon is a noble gas and it doesn't react. So he kept the detector for a while in the neutrino flux, and then he took out the detector and counted the number of argon atoms that were produced. Now that's a very difficult experiment, but Davis could take it up as a challenge because Davis had a chemistry background and he was a chemist and he knew very well how to distinguish between argon and the other material in the detector. What Davis observed was that the observed number of solar neutrinos is less than the number expected. The ratio, which should have been 1 if things had been all right, turns out to be 0.33 plus or minus 0.02, so 0.03. So this was very small. The error bar was small, and so this is clearly not in agreement with unity. The first reaction of physicists to this was that Davis is a chemist, and so he should not meddle into the affairs of physics, and he's probably wrong, and it should not be taken seriously. But after many years, this experiment was started in the late 60s, and then since Davis kept on doing his experiment and finding a small number, other experiments were started, and they too found similar shortfalls. Now, there are two ways, since the number of neutrinos produced in the sun can be very well estimated. So two things might be happening. One possibility is that neutrinos are decaying on the way to the Earth. So the number produced is certainly right, but the number we see is whatever is remaining. Part of the neutrinos have decayed. The other possibility is that perhaps neutrinos are oscillating to, electron neutrinos are oscillating to some other type of neutrino, maybe a muon type or a tau type, and the detector that was being used would be sensitive to only electron neutrinos. It would not work for muon or tau neutrinos. So therefore, it was missing whatever had oscillated into another type. So this was a question whether neutrinos had decayed or they were oscillating into a different type. How to look for that? The answer to that is, remember that we spoke about the Z boson mediated process, weak interaction, the neutral current weak interaction, which is of the same strength for all types of neutrinos. So if the neutrinos have just oscillated to a different type, and if you can set up a detector using the neutral current interaction, then you would see no change. But if the neutrinos had decayed away, then obviously something is lost and you would see a smaller number. Now, before I pass on, I have to remind you that Ray Davis, who was laughed at because he tried, as a chemist, he tried to do physics. Finally, he got the Nobel Prize in 2002, and the Nobel Prize was in physics, not in chemistry. So that tells the physicists to be a little more modest. So as I said, the way to test whether neutrinos have decayed or they have oscillated is to mount a neutral current experiment. And such an experiment was planned by Alan MacDonald at the Snow Lab in Canada. And he did such an experiment involving the neutral current, which was the disintegration of the deuteron. And he found that the observed number over the expected number is exactly equal to 1, which means that neutrinos have not decayed, but they have rather oscillated to some other kind. So the other experiment from which we got evidence for neutrino oscillation is the atmospheric neutrino experiment. in the atmosphere, lots of neutrinos are produced. Firstly, the atmosphere, due to strong interactions, pions and kaons are produced, and then these pions decay to produce muon neutrinos and electron neutrinos. Now, these neutrinos were first detected by the experiment in Japan of Masatoshi Koshiba, started in Kamiokande and Super Kamiokande under Koshiba's leadership, and Koshiba got the Nobel Prize in 2002. And from the properties of the atmospheric neutrinos studied on Earth, it was established again that neutrinos are oscillating, and this was under the leadership of Kajita, Takaki Kajita, who won the Nobel Prize in 2015. So I will not go into the detail of the atmospheric neutrino problem, but I simply state that this is another way to look for neutrino oscillations. So we have to ask ourselves, what is behind neutrino oscillations? And what is behind is simply quantum mechanics. Neutrino oscillation is a quantum mechanical phenomenon, but it's just like the oscillation of a pendulum. In the case of the pendulum, it goes from the left to the right and back again to the left. And similarly, in neutrino oscillations, as a neutrino travels, it becomes a muon neutrino, and then an electron neutrino becomes a muon neutrino, and then back again to an electron neutrino. And in this way, this oscillation process goes on and on. The characteristic wavelength of oscillation is the neutrino oscillation wavelength, lambda, and the lambda is proportional to the energy of the neutrino and is inversely proportional to delta, where delta is the difference in mass squares of the two types of neutrinos. So therefore, if the neutrinos are massless, or even if they have the same mass, so if the neutrinos are degenerate, then m2 square minus m1 square is 0, in which case delta is 0. And if delta is 0, then the wavelength becomes infinity, which means that one can never detect neutrino oscillations. Conversely, if one sees neutrino oscillations, as we have done, it implies that delta is non-zero, and therefore neutrinos have a mass. This is a picture of how oscillations take place as one moves in energy or in distance. So the background of neutrino oscillations is the following, that the mass eigenstates, which are the stationary states, and the flavor eigenstates, which are the ones which are produced and detected, like the electron and the muon neutrino, these are not the same. The electron neutrino is actually a superposition of two mass eigenstates, and the muon neutrino is the opposite, the orthogonal superposition of the same mass eigenstates. So when something like this happens, when the flavor eigenstates are not the same as mass eigenstates, then a simple calculation shows that oscillations take place, and the oscillation probability can be calculated and is given in terms of the mixing angle theta as 4 times cos square theta sine square theta and sine square pi L by lambda. Here, lambda is the oscillation wavelength, which we have already spoken about, and L is the distance of travel. So here I have a picture where this you can take as the distance of travel or the time of travel. And on this side, I have the probability. So to start with, there is only the electron neutrino, which has a probability 1. And the muon neutrino has 0 probability. And then as time passes, this probability decreases and this increases until this one reaches its maximum, and this one is minimum. And this oscillation can go on as time progresses. So from the neutrino oscillations, we know that neutrinos have a mass. The essential ingredients are that the neutrinos have a non-zero mass and they are non-degenerate. There is a mass splitting, and also that the mixing angle is non-zero. Now, from the results of the solar neutrinos and the atmospheric neutrinos, we can try to fit the result, the data, to obtain the best fit value of delta, the mass splitting, and the angle theta. It turns out that the results from the solar neutrino problem and the atmospheric neutrino anomaly give rise to very different values of delta and very different values of theta. So the delta from the solar neutrinos is 6 times 10 to the minus 5 electron volt squared, whereas that one from the atmospheric anomaly is 3 times 10 to the minus 3 electron volt squared. These are extremely small mass differences. Recall that in these units, in the electron volt unit, the mass of the electron is 500,000 electron volt. So the neutrinos, their mass splitting is extremely small. Now, when we have discussed neutrino oscillations, we have spoken of a mixing angle theta, but of course there are 3 kinds of neutrinos, and there are 3 flavors of neutrinos and 3 mass eigenstates. So therefore, in practice, the situation is slightly more complicated. The neutrinos can oscillate amongst themselves. And so the mixing matrix is not just one angle, it doesn't have just one angle, but in fact, it's like this. It has 3 angles and a phase, and it's like the 3 Euler angles, and the phase arises because in quantum mechanics, we have a complex wave function. So there are 3 angles and a phase, and many of them have now been determined, but not all yet. So what is not determined? What is not determined, for example, is the mass ordering. What do we mean by mass ordering? While we do know that in the case of the solar splitting, which is the smaller splitting, we know the sign of the mass difference, mass square difference. So nu2 is above nu1. What we don't know is the sign of delta atmospheric, delta m square atmospheric. So therefore, there are 2 possibilities. Either nu3 is above nu2 and nu1, which is called the normal hierarchy, or nu3 is below nu2 and nu1, which is called the inverted hierarchy. Is it the normal mass ordering or is it the inverted mass ordering? At this moment, we do not know. And this is a very important unknown in particle physics, and a lot of experiments are planned around the world to understand this question, to settle this issue. Now, one of the experiments is planned in India, and it's called the India-based Neutrino Observatory. It's planned in this location near the Tamil Nadu-Kerala border in Pottipuram. And to do any neutrino experiment, you need a rock cover. You need a cover, you need a shielding. So oftentimes neutrino experiments are done in mines underground. For example, in the Kolar gold fields, there was a neutrino experiment before in India. And also in other places in the world, neutrino experiments are done in mines or under a mountain. For example, here at Pottipuram, it's the hills, the Western Ghats, which provide a 1 kilometer rock coverage shield to block other particles. Because from the cosmic rays, you would get all kinds of things, protons and alpha particles and muons and so on. you want to cut them all off so that only neutrinos remain. And that happens if you go under the mountain. The strategy of the iron calorimeter detector at INO is that you would have a huge iron detector with a magnetic field. The magnetic field is critical because the magnetic field distinguishes between the charges of the particle. The mu minus and the mu plus can be distinguished. And the mu minus is produced from mu, while the mu plus requires an anti-muon neutrino. So one can effectively distinguish reactions originating from neutrinos and anti-neutrinos through this magnetic field. So using that, one can settle the question of the normal versus inverted ordering of neutrino masses. It's a very important experiment which was planned very early on, in fact, from the early 2000s, 2002 onwards. However, it has been stuck, and it has been stuck mainly in a legal quagmire. There have been legal cases, and it's been very difficult to get rid of these legal issues and start the experiment. It could have been the first one in the world to determine the hierarchy of neutrino masses. Before I finish, I want to turn to another feature of neutrinos, namely that the neutrino can be self-conjugate. It can be its own antiparticle. On the face of it, this might sound a little strange, but remember that the photon is its own antiparticle. There is no antiphoton. Similarly, there's also the pi0 meson, which is its own antiparticle. So we do know of particles which are their own antiparticle, self-conjugate particles. Of course, they have to be neutral because the antiparticle has opposite charge. So therefore, a self-conjugate particle must be neutral. And the neutrino is a neutral particle. So this question is meaningful, whether the neutrino is its own antiparticle or not. At this moment, we do not know the answer. We do not know whether it is its own antiparticle or not. However, I should discuss with you the way we can find whether the neutrino is its own antiparticle or not. The way to do that is through what is called the neutrino-less double beta decay. First, I have to tell you what a double beta decay is. In a double beta decay, it's like a beta decay, but here 2 electrons are emitted. And of course, with the 2 electrons, there will be 2 anti-neutrinos. These should have been anti-neutrinos. So 2 anti-neutrinos would be emitted. Now, if the neutrino is its own antiparticle, if it is a self-conjugate particle, then the 2 neutrinos which are produced can in fact kill each other. And therefore, in such a situation, there would be no neutrino in the final state. So if the neutrino is its own antiparticle, then neutrino-less double beta decay is allowed. It turns out that if one does the calculation for such a process, then the neutrino-less double beta decay is proportional to the square of the mass of the neutrino. Now, how do you look for neutrino-less double beta decay? For that, you have to go back to Pauli's original proposal. Pauli had proposed the neutrino by looking at the beta decay of atoms, and he said that since the electron is not coming out with a unique energy, there must be something else which is carrying away the balance energy. In this case, in the case of neutrino-less double beta decay, there is no neutrino in the final state. So therefore, we have now come full circle, and therefore now if neutrino-less double beta decay takes place, the sum of the energies of the two electrons must exactly match, by conservation of energy, must exactly match the difference in masses of X and Y. So what you do is you look for an element which undergoes double beta decay, and you look for a peak in the two electron total energy in the hope that neutrino-less double beta decay has taken place. And if you see such a peak, then you have established that the neutrino is a Majorana particle. At this moment, we only have an upper bound. No neutrino-less double beta decay has been seen. Many experiments are trying, ongoing experiments are there, and the current limit on the neutrino mass is a 0.2 electron volt from these experiments. Now, of course, if the neutrino is its own antiparticle, then lepton number will be violated, because the neutrino carries a lepton number 1 and the anti-neutrino has a lepton number -1. So therefore, lepton number will be violated if neutrinos carry, if neutrinos are self-conjugate. Before I end, I want to touch upon how neutrino masses are generated. As I have already discussed with you, in the standard model, there is no right-handed neutrino, and the neutrino is only left-handed, and therefore the mass of the neutrino is 0, because you need both the left and right in order to write down the mass term. And so therefore you have to introduce a right-handed neutrino in order to generate the mass of the neutrinos. And that is, introducing the right-handed neutrino is not enough. You also have to explain why the neutrino mass is so small. That is another enigma for us. And for that, so the mundane way is to add a right-handed neutrino. This solves the problem, but it has no explanation of the smallness of nu. So nowadays, there is a lot of excitement about what is called the seesaw model of neutrino masses. The seesaw model says that the neutrinos are light because in the theory there is some other heavier mass which has an inverse proportionality with the neutrino mass. And therefore, the smaller the neutrino mass is, the larger the M is, and vice versa. So it's like a seesaw. If you make M very large, then the small mu will be very small. A lot of excitement is now on for these seesaw models. So finally, looking ahead, what is the mass ordering of neutrinos? Is it normal or inverted? We do not know at the moment. Is there CP violation in the neutrino sector? This is a question which I did not discuss, but a lot of experiments are now on in Fermilab in the US and in Japan and elsewhere to look for CP violation in the neutrino sector. It is important to understand the interactions of neutrinos with matter, because that affects the mass of the neutrino. The interactions make the mass of the neutrino different in matter compared to in vacuum. For example, as we know, for light, the velocity is less in matter compared to in vacuum. And similarly, the mass of the neutrino is different in matter. And that's an open question which is being studied. Majorana neutrinos, one would like to know whether neutrinos are self-conjugate particles. INO, the India-based neutrino observatory, is an experiment which is being planned in India. It is a unique one with a huge magnetic detector. We hope that it will soon start operation. And then there are questions about explaining neutrino mass, the different models of neutrino mass on which there is a lot of activity. And then there is new physics, new interactions and symmetries which have to be imposed to get the right model for neutrino mass. And finally, something I did not touch upon is the role of neutrinos in astroparticle physics, in supernova, in nucleosynthesis, and so on, which is a major subject in its own way. Now, I have taken you on a ride through an important part of particle physics. I want to end with this cartoon. So here is this drunk person sitting on a staircase, and here is a curious passerby who is asking him, "What happened to you?" And the drunk says, "Quarks, neutrons, mesons, all the quarks, neutrinos, mesons, all those damn particles you can't see. That's what drove me to drink, but now I can see them all." So thank you very much. I don't suggest that you take to drink. I suggest that you take to neutrino physics. Thank you very much.
Thank you, sir. Thank you very much for this wonderful talk and the very nice overview. I will now take some questions. Is there any questions from the audience? Please write down in the chat box.
I see one question. Is there any signature of relative phase between two mass eigenstates? This is a relevant question. I did not talk about the, there is a phase which appears in the matrix which takes the mass eigenstates to the flavor eigenstates. Now that phase is a very important one because it is responsible, anytime there is a phase, it is responsible for CP violation. Coupling constants or masses have to be complex in order for CP violation to be present. So there is an indication that CP violation might be there, but there are many experiments going on, and so far there has been no clear detection of CP violation, though there are some indications, not very settled yet.
Okay, so is there any other question to sir? Sir, there is another one from Aparajita Bhattacharya.
Mass of neutrinos should necessarily be very small. Yes, it has to be because you know, this is something which certainly the mass splitting has to be very small from neutrino oscillations, but even otherwise there are attempts to measure the neutrino mass using, for example, tritium decay. Tritium is chosen because tritium has a very small Q value. If the Q value is large, then the neutrino can be emitted with a lot of energy. But if the Q value is small, for tritium, the Q value is of the order of a few keV. So therefore, it can be used as a probe. And what you have to do is to plot the Courier plot of the electron energy, and it depends on the curvature at the end that determines the mass of the neutrino. So from that experiment, from the tritium beta decay experiment, we know that the neutrino mass is less than 0.2 electron volt. Another similar experiment is being carried out at Troitz in Germany. Now it's ongoing, and we are awaiting the result from that experiment. So also cosmology indicates that neutrino, the sum of the neutrino masses has to be less than a few electron volts. So neutrino masses have to be very small, just to set the scale, have to be less than a few electron volts, whereas the mass of the electron is 1 million electron volts. So it's really very, very tiny, very, very tiny.
Sir, may I ask you one question related to this question?
Yes, yes, please.
So and the point is that whatever the models we are building is a high energy model, right? So if the absolute mass of the neutrinos are really very small, and if we talk about the hierarchy in the energy scales, then it has to be come from very low energy physics, right? So in that sense, I mean, I feel a little disturbed. I mean, how do you explain?
Not necessarily, Dr. Mukherjee, because, you know, these are technical matters and I did not discuss. But remember, in one slide, I talked about the seesaw mechanism.
Exactly.
The seesaw mechanism is a
Okay,
way in which one heavy scale can give rise to a very small scale.
Yeah.
So that is the key.
Okay, thank you.
I have another question from our student Rishabh Gupta.
Yes,
Sir, are there new methods to detect neutrino more precisely?
are there new methods to detect neutrinos? Yes, I mean, this is it. I think people like Rishabh will contribute to these things in the future. It's a continuously evolving process. How best can you detect a neutrino? Because neutrinos are so weakly interacting. Very clever methods have to be devised to detect neutrinos. So you have to look for a reaction when the neutrino produces some particle. And right now, the latest technique is liquid argon. When neutrinos produce, let's say, an electron passing through liquid argon, then liquid argon detectors are the most modern ways to detect neutrinos. Another experiment, Super Kamiokande, it uses a huge volume of water, and it uses Cherenkov radiation, which is emitted when the neutrino produces an electron, and that passes and emits Cherenkov radiation. So it uses photomultiplier tubes. So many clever things are being devised to look for neutrino interactions, and surely the youngsters will contribute to that.
Okay, sir. Thank you so much.
Thank you very much.
I will request Professor Pandey to end this session. Sir, are you here?
Yes, Purva. So I would like to thank again each and every participant. And this is with a promise from all of you and on behalf of Sobhas that one day soon we will invite Professor Raj Chaudhary to our campus to interact with our students and faculty members. So thank you everyone. And I think more sessions to come. We have
Yes, sir.
a series of lectures.
Yes, sir. Professor Arup Kumar Rai Chaudhary is already with us. Welcome, sir, to this conference.
Thank you.
Okay. And thank you, Professor Amitabh Rai Chaudhary, once again. And so we are going to take a tea break, very small tea break for 15 minutes. And we will join once again at 11:15. So see you all there after the tea break.
Thank you.
Thank you, sir. Thank you.
So may you call
Thank you, sir.
Arup, sir. Is he informed that it's a 10-15 minute break?
Yes, sir. Yes,
okay.
It is already informed.
Good.
Okay.
Good morning, Professor Rajendra. Good morning, sir.
Yes. Professor Sarkar, thank you.
Yes, sir. How are you, sir?
I'm very fine.
So it's really
must congratulate you and your colleagues for organizing this meeting. Most importantly, I was looking into the list of the contributed talks. Your 10-minute talks. They're really good, and there's a variety of things that you have attempted to really get in. See, I think it's a very nicely organized meeting. And we are kind of apprehensive that in the time is so bad that how things can really be assembled, but it did work out, and nice to see so many people.
Sir, actually, sir, it's really possible due to only blazing off of yours just
नहीं नहीं हमारा कुछ नहीं है भाई हम क्या है हम तो आई एम सिटिंग इन माय रूम दैट इज ओनली
yes,
doing
sun is on the just center of the universe, but we are on the earth.
कुछ नहीं so maybe we can have a cup of tea all of us and then assemble after 10 minutes.
Yeah, yes. Okay, sir. Thank you.
Purva madam, can we announce that for that general feedback form? I'm
I
sending.
will announce it before the lunch break.
Okay.
Okay, I have the link and I will just announce it up just before the lunch break. Is it okay,
Okay.
Tapya?
Yes.
Okay.
Should I be getting ready? Yeah, thank you.
Good morning.
Good morning, Apajita. How are you?
Fine. How are you?
Fine.
Okay, stuck at home.
Yeah, I'm not exactly stuck at home, but today I'm at home.
Yes, we are having some.
Okay, so welcome you back all. So we are going to start our second session, and here we will have two invited lectures from Professor Arup Kumar Raichaudhury and Professor Bornali Ghosh. Professor Arup Kumar Raichaudhury is here, and also Professor Bornali Ghosh is also here. Welcome you, sir and ma'am, to our conference. So may I now request Professor Moumita Mukherjee to act as the session chair. Professor Moumita Mukherjee is currently Dean of Research and Development in Adamas University. She was awarded her PhD in Radio Physics and Electronics from University of Calcutta. She did her doctoral and postdoctoral studies under DRDO, Ministry of Defense, Government of India. She received visiting scientist and postdoc position from INEX Newcastle University, UK, and Technical University, Darmstadt, Germany. She was attached with DRDO Center under Ministry of Defense, Government of India as scientist reader grade with a total 17 years of R&D and teaching experience. She is visiting and adjunct professor at JAP BMI under Calcutta University and the West Bengal University of Health Sciences. Her research interest is focused on the terahertz electronics, semiconductor devices, graphene electronics, photosensors, nanobiosensors, and medical electronics and instrumentation. So, Professor Mukherjee, over to you.
Thank you, Dr. Purva, for your nice introduction. Now we are in the second day of National Conference in Frontiers in Modern Physics, and we have already met a good number of speakers yesterday and today morning as well. So this session will start with the mind-blowing and very thought-provoking lecture by Professor Arup Kumar Raichaudhury. Now, a brief introduction about our speaker. Professor Raichaudhury obtained his MSc degree from IIT Kanpur and PhD from Cornell University. He had postdoctoral experience at the Max Planck Institute, and he served as the director and distinguished professor of S.N. Bose National Center for Basic Science. Prior to joining the center as a senior professor, he worked as a professor of physics in Indian Institute of Science, Bangalore, and as director of National Physical Laboratory, New Delhi. His research interests spanning a period from 1976 till date and covered a broad canvas of problems in condensed matter physics and material physics. This includes physics of galaxy state, metal insulator transition in oxide, physics of high transition semiconductor, superconductor, and magnetoresistance. His research activities encompass synthesis of material of different kinds, fabrication of nano devices, and physical measurements done down to low temperature in high magnetic fields using a variety of techniques involving electrical, magnetic, and optical measurements, as well as scanning probe techniques and electron microscopy. During his tenure as the director, most of the important experimental research facilities, including the technical cell that houses the sophisticated instruments for common use in the center, was actually established. Professor Raichaudhury is the nodal officer of the prestigious Technical Research Center project of the center. His group in Indian Institute of Science and S.N. Bose National Center for Basic Science had graduated more than 35 PhD students who are now established researchers, academics, professionals in India and abroad. His research work is widely cited. He is a recipient of Shanti Swarup Bhatnagar Prize in Physical Science and is a fellow of all the science academics in India. Professor Rai served in a number of national committees that include Science and Engineering Research Board and Program Advisory Committee on Solar Energy Research Initiative of the Department of Science and Technology, Government of India. He had been a member of the Science and Engineering Research Council of the Department of Science and Technology and chaired the PSC on condensed matter physics and material science. He also chaired the FIST Advisory Committee of Department of Science and Technology on physical science. He has served as the member of Board of Governors of IISER Pune and IIT Kanpur. So with this brief introduction of our today's speaker, I will request, sir, for a thought-provoking lecture for all the attendees of to today's program. And in coming 1 hour, I believe we will get enriched from the lecture. Over to you, sir.
Thank you, Professor Momita Mukherjee. I'm sorry, my video exactly is not in good mood today. So, I cannot shot my video, but one way, it is good that you cannot see the face. You can see the lecture. So, I must say that I'm no longer in Lesson Center. I have been last couple of years, I'm associated with CGCRI. So, there are a few changes here and there. Now, I can do this share screen now, right?
Yes, sir.
Yes,
Please.
sir.
Okay. Okay, are you able to see me? See
Yes.
the thing? Okay.
Yes, sir.
Yes.
So I must thank all of you, and particularly Professor Sarkar, for getting this beautiful conference going in. I had a very good experience of visiting the university, I think 3 years back on February 13th, what is my calendar shows. And it was a nice interacting with you at that time. I did talk of a very different topic at that instant. Today, I am going to talk on an issue that we have been working for last 20 odd years. And I don't know how long we'll continue into this. But the important point is that I need to bring to focus the important thing, which is the necessity of physical measurements. Now, the first few slides, I'll just show why we need to do that. And then particularly in the area of nanoscience technology, I'll be telling you that is why we should be, and we need to do physical measurements on single nanowares. And we will be giving you some examples spanning over last 15 odd years, the type of measurement that we did. Now, the first thing that I should like to talk about is definitely the why should we do physical measurements? Then why it should be done at the level of single nanowire? What is the advantage you get? And then how do we do the experiment very briefly? And then come to the main part of the topic, that the examples of single nanowire experiment and what we basically learn from them. And I'll do the talk in the style of walk the talk, so that some people may call it storytelling, but it's not exactly storytelling. I'll embed our work in the manner of storytelling. Okay, and so let us see now. So the important point is that why do we do physical measurements? I think if you look into this part of the cartoon, is very clear that one accurate measurement is worth 1,000 expert opinions, and that's very important. And we should realize that if you do physical measurement with the stated accuracy, and what do you mean by traceability? Traceability means traceable to physical standards, is at the core of human civilization, and it is becoming more and more important in the modern era. And you know that there's a meter convention that we follow, that is where all the physical measurements become traceable. But I'll not go into that aspect of physical measurement, but rather I focus on that we need to do precise physical measurement, but it's one of the prime requirements of science and technology. For, even when I was looking into the talk of Professor Amitabh Rai Chaudhuri, this whole neutrino experiments is actually very high precision measurement. And all our understanding will follow from the type of measurements which are done there. There's also yet another important thing that we don't realize, that whole of international trade is dependent on physical measurement. And I'll just throw you a couple of examples to show that there will be no international trade if there is no physical measurement. Now, coming to very precise physical experiment, the understanding of the world came from that. I think one of my most favorite experiment is the Michelson-Morley experiment done in 1887. And it's a negative experiment. It attempted to existence of ether and couldn't find any. And you know that it was essentially based on, is a high precision experiment based on Michelson interferometer. And they wanted to detect about 3% of the fringe shift, which they couldn't. And that shut down the ether. We went into a different category altogether. And if you look into the expression of the time, you can easily see 1 minus v square by c square coming over there. And that is your time contraction. And this actually led to the special theory of relativity. So this is an example of how a high quality precision experiment actually changed our understanding of the world around us. Now let me come to something very mundane. We are not Michelson-Morley. We are not going to do that kind of experiment, but I want to buy copper wire for wiring my home or someplace, or I want to do an experiment. What do? When I do in a lab, I want to buy a copper wire, maybe it has a gauge and 42, 44, 32, depending on how thick a wire you want to use. I want to know how much is resistance per unit length. I don't have to do anything. I just have to measure its area, which is also there in the conversion table of gauge to area. And from that, I can quickly find out what is the resistance per unit length. For someone has tabulated for me the resistivity of copper, or for that any metal. If you go to the standard database of National Institute of Standards Technology in USA, which is to known as NBS before, they have voluminous data of any resistivity, or for that matter, any physical quantity that you need. So someone measured it and created the database. But what is interesting thing and what is important about physical measurement, when you combine it with a theory, that gives you a predictive power. And that is what is the important thing. As a physicist, you should realize, if you combine the correct experiment with the correct theory, the power of the measurements go up by orders of magnitude. Let me take this very simple example and ask that, can I predict temperature dependence or resistivity just from the room temperature resistivity in a conventional metal? Very simple question. Someone brings to me a material which I know what it is, and it tells me its resistivity is 5 micron centimeter. Fine. He wants to know the resistivity, all the whole temperature. I can measure it, but I can tell him quickly if I know one aspect, what is the Debye temperature of that material. So let me just flash this data. This has been taken from web. This is a copper alloy with nickel being put in, resistivity goes up and all that. But I need to have two theories at my disposal. One, the Matheson rule of electrical resistivity, which tells me if I add the thermal temperature dependent electron phonon interaction with the residual resistivity, which is occurring here, the rho naught, then I can predict the whole thing. So now if I know this part, I can then know what is the resistivity of room temperature. Conversely, if I know the resistivity of room temperature, I can really find out what is the temperature dependence of the resistivity. Sorry. And I know that the temperature of dependence of resistivity goes by just one very important theory. There's the Bloch-Gruneisen theory. It has one parameter, namely the Debye temperature, and rest of things follows from it. So this red line is nothing but the Bloch-Gruneisen theory. So if if someone gets me a platinum resistance thermometer, I just measure the room temperature resistance, and I can tell him what is the resistivity going to look like as a function of temperature. And the whole table can be done. If you look into some handbooks of temperature measurement, this is exactly what is stated there. So that is the importance that I have measurement, and we have valid, very predictive power coming up from very good theories which have developed over the years. Now, I flash one thing, how it is important for international trade. Just take one example, Airbus industry. This data is slightly older, but about €1 billion worth of Airbus parts are outsourced from India. It's going on for a very long time. And believe me, the A320 door worldwide, half of them come from our Bangalore Hindustan Aeronautics Limited. And there's another Bangalore company called Dynamic Technology. it makes the flap tracks beam for the A320, and they are going to now to A330. Now let us ask a question, where did the measurement comes in? It comes in here. For if I make a door by HL, take it to the Toulouse, which is where the factory of Airbus is, and then after arriving there, I find it is not fitting, then this is not exactly what you want. So at the core of it is that you got to have calibrated physical measurement, otherwise everything comes to a knot. So it is not only just very high precision physical measurements that are needed for practicing scientists, but it is also needed for much broader activities that spill over to economy. I take one more very important example of science of that I call it now the necessity of physical measurement, just time measurement. This was actually I learned many years back through a talk that suppose 2 aircrafts are entering Indian space, and there are 3-4 radars looking at them, and the time resolution has to be better than a millisecond or a microsecond to identify which aircraft is the enemy aircraft or which aircraft is not not an enemy aircraft. So you can see immediately precision physical measurement is a necessity. Okay, now I move to the next part, that why should I be doing a physical measurement on a single nanowire? Okay, I understand that it has to be done, it's good for international trade, it's good for science and technology and everything, but now I have to convince myself that I should be doing the physical measurements on a single nanowire. So why should we be doing it? There are quite a few reasons. I'll bring it out with examples that if you make measurements on a single nanowire and allow us to investigate even qualitatively without the associated problem of size dispersion and interaction, you got to do the measurement on a single nanowire or a single nanoparticle of that order. I call it fallacy of average. But average all the time doesn't work. Average many times does fail. And I'll bring that out, and that is where you cannot do an experiment on an ensemble and reach a decision. So you have seen that I have given the example of how Gruneisen theory and all that gives that fantastic predictive powers which have been developed for the bulk. I like to see if they're valid into the regimes of few tens of nanometers that we'd be working on and have some predictive power. That is what I call crystal ball. Well, there's something very interesting you can do. A bit of a jasusi, a bit of a Feluda kind of activity, that there's some unresolved issues. You can really solve it by doing these measurements at single nanowire level. And at the end, I like to really smash on something. The small is not just beautiful, small is amazing. You get ultra high sensitivity, amazingly new phenomena coming in the moment you start doing experiments with single nanowire. So this is exactly what will constitute my next part of the talk. That is why by taking this, the 4 bags or 4 examples, I like to excite the share with you the excitement of this kind of measurements, which are difficult at times, which are very rewarding at the end. But just I'll flash on a couple of things, that how do you actually do the measurement on single nanowire? And there are 3 aspects of doing physical measurements on a single nanowire. You have to grow the nanowires, and you like the nanowires to become long, like this boy over here, but at the same time we like it to be narrow. I'll not grow much into the growth today. I understand Professor Barnali Ghosh will be talking after me. She'll flash few things in her talk. Then you have to make contacts to them, particularly if you do electrical or optoelectronic measurements, and that's a difficult part. And that is what we call agony, but you have to pick a needle from the haystack. And at the end, you make the measurements, learn the physics, and at the ecstasy moment, but you are revealing the truth. So these are the 3 things that I'll be covering on during my talk. And the first 2, namely the growth and the agony, I'll be just touching on, presenting more on the measurement aspects and in the ecstasy part. Now, this work that we're presenting, actually culmination of nearly 20 years of work that I've been working on nanowires. For most of my activities in this field have actually been on nanowires. There are other things I do, but the main focus is on there. And it started with an ensemble of nanowire and complex oxide in Bangalore in 2001. And then Avik Bede and Achyut Bora, they did work on metal nanowires. Avik is now a faculty in ISA Bangalore. And then Dr. Sai did work on field-assisted vapor phase growth of nanowires. When I moved to SNO Center in 2004, we started working on template-grown metal nanowire of very high crystalline quality. And then we did field-assisted vapor phase growth. Dr. Rabia did. Venkat is down in Uppsala. And then we have, metal-assisted chemical etching to grow silicon nanowire. And we have 3 persons who worked on that. And then our recent work has been on chemical vapor deposited germanium nanowire. And you can see most of them are now doctor, and a couple of them are Mr. Shaili is now in ISC, and she is going to UCL, University College of London, in next February. So, they are just going into various places. Professor Ghosh will discuss a very important area of hydrothermal growth and pulse laser growth, and she'll flash it in her presentation. Now you come to it that, okay, we have said that we have grown the nanowires, we have, have the dream that we want to do experiment with them. Now, if we look into the various ways the nanowires are grown, there's one hand you have the very costly vapor deposition methods, the other hand you have the chemical methods. But important thing, the chemical methods are very compatible, they can really grow in large areas. And another important thing is that if you make these nanowires yourself, synthesize them, you can make them compatible with your measurements and applications. So I just flash on a couple of examples and go into our measurement part mainly. This is our latest work where we grow single crystalline germanium nanowire by vapor phase. It's fairly easy to grow that, you have a tube through which argon gas comes, you evacuate the tube with a pump, and then you put to see that the oxygen does not oxidize the germanium. You have one port where germanium is kept, and you have a slightly colder part of the furnace where you have a silicon on which you have gold nanoparticles. And after some time, when the gas goes, you get the germanium nanowire grown onto them. And this is better than more sophisticated methods where you use toxic germane, and it gives us this kind of germanium nanowires, which are typically in the ballpark of maybe 30, 40 nanometer to 100 nanometer. That's the size range that they go. And they're fairly good single crystalline. You can see from the transmission electron microscope, because the lattice fringes, this is the wire. You can see that this is about 30 nanometer, and it's a pretty pure wire. This is a Raman thing, and you can see that it has a 300 nanometer Raman centimeter inverse Raman shape that shows you that it's a high quality germanium nanowire. One nanowire growth method you have extensively used was growing them by various methods. For conventional metal nanowire, we used electrochemical deposition in commercially available, mostly aluminum oxide template. There are companies which sell it, and this diameter of this hole in a given thing can be from anywhere from 15 to 200 nanometers. Now, but it is not dispersed, that if you buy a template, it will be either 15 nanometer, 20 nanometer, 30 nanometer holes, but all the holes within plus minus 10% have the same diameter. And you can see that the thickness is about 60 micron, and there are straight down the lines going. So you have to just fill up, and you can do so by electrochemical deposition, put your electrolytes, fairly easy. You have a platinum electrode over here, and you have this reference electrode sitting over here, and you have the working electrode where you are growing it. So it's not that difficult. Or what we initially did when we have much sophisticated setup, we just soak the membrane with silver nitrate when you grow silver nanowires, put them in the copper base, and just have a needle and then put it over there. And in a small area, you just within a few seconds, you can grow the nanowires. And if you look into the nanowires, you can take out the template by simple KOH etching, and the stack, you can see all the nanowires. Like you have one good growth, one full thesis is done. Like you get, it's just there. You just cannot do anything, and they are high crystalline quality. If you do selective area electron diffraction, you can see that. So this is the two types of growth that we have talked about. We have also done very recently another type of growth, and which is using various forms of electron beam or ion beam lithography. And this is for making photo detectors, where you have a silicon oxide And then there's a silicon. We want to make a device on that silicon. So what we do is that actually make micro lines. You can see that they're typically around 1 micron. They're not that nano, but underneath this thing, we have to etch out the SiO2. That's very important. And that is where all these things came, and they give you a fairly nice photo detector. So this is as far as the some part of the growth method goes. Now let us now come to making the contact part. Again, I'll be going very quickly through it. And the way we do it is that we generally take a wafer, which is a silicon oxide on silicon. Then you have these contact pads evaporated by either lithography or by hard disk. And then in this particular area, we put a drop where you have all the nanowires, and then come and make the connection to this by electron beam lithography or focus ion beam lithography. You can see the here is a single nanowire with a 30 nanometer diameter, and the separation of the electrode is about 200 nanometer. So this is the type way we start doing electrical measurement of single nanowire. So there's a growth part, there's a connection part, and this is what we used in our nanolithographic setup. We are set up over the years, and this machine was installed in 2009, and we put it in a clean room a couple of years after installation of the machine, and it has given all the work that we did over the years using this particular machine. You have the ion beam, you have the electron beam, and you can work with it. Let me just give you one example of a device. I'll be talking about it afterwards. And this we made a very ultra-sensitive photo detector of extremely high responsivity using this silicon nanowire. They are simply made by what you call the metal-assisted etching. Like you put some metal nanoparticles on the silicon, then put them in a particular HL solution, and you get these nanowires coming up. It looks like an elephant walked through a sugarcane field. So you have broken wires and all that. But if you're lucky, you can pick up a good wire, and then you can make a optical detector. You can see these leads. These are 500 nanometer leads, and the wire had 80 nanometer diameter. And you can see this. I show just to show the agony. You made the device, but then you find that somehow it has snapped up. So you have to have redundant electrodes so that you can do measurements even one part gets snapped up. So this is just an example of the type of things that we use for our measurement. So let us now come to the measurement part, and let us see how we do the measurements and what type of results we get. So let me first take the fallacy of average. And the fallacy of average we have learned in a hard way. It's not that someone told us that you can get all kind of results if you don't take the average correctly. But we learned it in a hard way. And that is where I'll share you where the hard learning comes. So we started with a, if you start with a, say, jungle of these nanowires, you can see you have thin nanowires, you have thick nanowires. And the question that you are asking, that if I know the size distribution, like maybe Gaussian, log normal, whatever, and from this, can I really rightly say from the main thing that I can connect the average physical property to the average diameter? So that's the question. As most of us do that, we say that I have, say, physical property, say transition temperature or something like that, or resistivity, whatever, and then say that this is the average value I'm getting. Can I say that this is my average diameter of the nanowires I have grown, and this is how they are connected? And let us now see what may happen. See, if we have a very nice linear dependence of the physical quantity with diameter, it doesn't happen most of the time. Then if you take an average, then you can put this distribution anywhere, more or less you'll end up getting some kind of a value, and you can say the average in this case is meaningful, maybe. But let's look at this graph. And I'll show you a physical situation, what happened. But the physical thing has a up and down. It goes up, then comes down. Now, can you define an average here? Now you can put the distribution here, you get one value. Put the distribution here, you get another value. Put the distribution over here, you get another value. So when you say that I have an average diameter, and this is how the average physical quantity depends on the diameter, you can at best be wrong. So this is where the fallacy starts. Let's now look at a quick data. This is the first experiment on our nanowire that we published in 2004, and it was done by on a complex nanowire. Let us see, we wanted to do some experiment with it. This is a material many years of work on. It is called LCMO, and I'm not going into the details. We grew this nanowire within the alumina template. It was not easy to grow, but the grown was done. And you can see that this material, where it shows a ferromagnetic transition, it also has a peak in the resistivity. This is the data taken on a bulk single crystal. But now we did this experiment on this single crystalline LCMO nanowire. They're within the template. So we measured the acid susceptibility, and at the time we didn't have much of an apparatus to even measure susceptibility. It was just a simple coil made by Shoini as a part of our MSc thesis. She's now an associate professor at Cambridge. So, I think it's a good thing that she did that. So, and what we found it very interesting, that the TC has shifted by nearly 50 degrees when you have gone to the nanowire. We published the paper, and then immediately the hell broke loose. And the reason is that if you look into the conventional ferromagnets like a nickel, the TC decreases when the size is reduced. It's known as finite size effect. But then everyone said that kuch galat tha, there's some mistake, etc. Some people remeasured it, they supported us, but some people remeasured it, they said no, we are getting ulta result, that the TC decreases on size reduction. Some people are even more benign, they said bhai kuch nahi hota hai, TC size ka side depend nahi karta hai. So the situation became really screwy by the time I moved in SNCO Center. So at that time, Tavadi Sarkar joined us for PhD. It took us a long time to size select the particles. And we did the measurement of the, don't mind the sound, there is some work going on at the, near my house, and that is where all this sound is coming. So sorry, I have not much of a control on that nuisance. So, you can see the red dots, the TC were measured by using the Druva reactor, neutron scattering. I am grateful to Yusuf for that. And the black dots are by measuring the magnetization. Now, how did we do the size selection? I'll quickly mention you. So this is the main data, that when you make a nanoparticle of a size within maybe 45 to 55 nanometers range, the TC has gone up. And when you have the nanowire which is size separated, and how did they do the size separation? No big equipment. Size separation of magnetic nanowire is much easier than you think. See, what happens is that suppose you're sitting at 300K, and there's a dispersion of these nanowires, or maybe just in a powder, you have all these guys sitting over there. Just take a magnet and just pull it across the beaker, wall of the beaker. What will happen? The nanowires which have a TC higher than 300K will stick to it, otherwise will not. So now you put it in a some kind of a slightly chill it down to a little below room temperature, slightly warm it up, that you really can size separate if the TC is around the room temperature. That is precisely what we did. No big equipment, nothing, just little bit of a work, but that is what we did. One thing I learned in my life, when you face a problem and you have nothing with you, you become innovative. When you have a problem, you are given a lot of equipment, you become uninnovative and start not thinking about it. So sometimes it helps if you don't have too many equipments with you. So, like we did that and we got this graph. This graph, you can immediately see that TC goes up and then comes down, and there's a physics to it. I will not go into it, but this is precisely what had happened. Look at this graph and this graph. That is, those who are getting the TC going up with particle diameter, they were measuring this part. We have principally measured on this part. So to us, TC was increasing as this is down. And then there are guys who are just sitting over here, to them TC didn't change. So we really then solved this fallacy by the diameter distribution business, and then learned that taking average in the wrong way can be absolutely disastrous when you come to this field. And we started thinking about single nanowire measurements at that time. So then the question came that can you do TC measurements on a single nanowire, the complex oxide? But the problem is that you need very high quality oxide, and Professor Ghosh along with his student drew the nanowire, And we make this connection to the single nanowire and made this measurement, measure this resistance. As I told you, this material show a peak in the resistivity at the ferromagnetic transition. And you can see that if 15 nanometer, if I take the bulk, its TC is 250K. It has gone by nearly 85K up by making it nano. And this is a single nanowire measurement. So there's no no things, you can say. Now, why we do the resistivity measurement on magnetometer based measurement with the single nanowire? Because if you calculate the magnetic moment in single nanowire, which is 10 micron long and 50 nanometer wide, the moment that you get is in the range of 10 to the minus 9 EMU, maybe minus 10 EMU. The best squid that you get stops at minus 8. So you are below the range of the best squeeze that you do. That's why you do the single nanowire resistivity measurement. And this is the result that we show just to tell that, we do get variation with size, the TC. And now we exactly know that what we saw in 2004, that the TC really goes up when you make it a nanowire, is a correct result. So this is what I would finish by saying, that from the agony of having wrong averages and trying to sort it out, we learned a lot. Now let me come to the crystal ball part, that can we give a predictive power developed for the bulk. And this is the work we published in 2006. It was the thesis work of Big Beat. And what we did is very simple. We just asked this question, that Bloch-Gruneisen theorem, which is used for bulk solid, is it applicable to the nanowires with the diameter at 15 nanometer up? Or we could grow nanometer down to 15 nanometer at the time. If we grow smaller, then maybe it will be valid even then. So let me see how we did the experiment. At that time, we could do the single nanowire experiment. So we grew it in the template, as I have shown you. Just put the top and bottom electrode and made what is called a pseudo 4-wire measurement. And we started getting results. And again, it is a very high quality oxide metal nanowire, and you can see diameter is 15 nanometer, and you can see the lattice fringes over here that shows you that is a good crystalline quality, the electron diffraction and all that. Okay, now this is the result. This is the resistivity as a function of temperature with 15 nanometer to 200 nanometer. How does the bulk look like? The bulk will come somewhere here. So by the time you are 200 nanometer, you are like a bulk. And now we started thinking that how to analyze the data, etc., etc. And let us see what we get. Obviously, the resistivity has gone up when you go to 15 nanometer. Now there's a temperature dependent part. Question is that, does it follow Bloch-Gruneisen theory? And there is a part over here which is coming from the scattering from the surfaces. There's also a classical theory there called Sondheim theory, and we show that theory is valid. I'm not getting into that to avoid many more details. But the interesting part is that when you go to 15 nanometer and you come to room temperature, you can see the resistivity. Half of it is the electron-phonon interaction, half is coming from the surface scattering. Okay, let's see how we can quantify and analyze the data. So try to see whether we can apply the Bloch-Gruneisen theory. So this is the theory. Now, if you look into this expression, it's a fantastic expression. There's only one parameter, electron phonon, that alpha electron phonon, that written over here, it contains E, H, C, and all that for a conventional metal, nothing more than that. And then you have a quantity, which is the divide temperature. So if I can fit the data of resistivity to this thing, I can get the divide temperature. But the nanowires, I don't know what the divide temperature. So let us see what we did it. We really fitted that. And you can see how good the fit can be. This from 1 Kelvin to 300 Kelvin, this equation, just fits it, n equal to 5 in this case. And you can see the high quality of the fit. It's only plus minus 0.1 or 0.2% is the order of the deviation that you get. Now something very interesting, when you have this kind of theory with a single parameter, you look at it, it is T by theta R. So, if I take the A part out, the temperature, the residual part out, and take all the materials which follow Bloch-Gruneisen theory, I can really collapse all the data into one single curve by scaling the temperature of the theta divide. And this is precisely what has happened. We have here silver film, we have here 50 nanometer silver, we have copper, 30 nanometer copper, 200 nanometer silver, everything. All the data collapses. Now, film is a bulk. No, God's sake, is it 200 nanometer, 300 nanometer film? They're bulk. 200 nanometer is almost like bulk. So what it shows us that this single parameter theory, which we call Bloch-Gruneisen theory, is valid in the nanowatts. And it also gives us a way to measure the size variation of the Debye temperature. You can see that this is the Debye temperature in the bulk, the Debye temperature nano regime. And for the FCC material, you have one kind of dependence, for the HCP another time. Now, there are theories that has been developed after this, which explains this data. And so, you can immediately see that the measurement that we did not only sorted out this problem, but it also sorted out the important issue that how to find the Debye temperature. Let me now go back to this data and show you where the predictive power becomes important. Suppose someone has made a silver nanowire of 30 nanometer, fine. And he wants to use it in some experiment to measure as a lead in electrical resistivity and all that. So now he doesn't have to sit down and measure it. It's not possible all the time. So he knows that the room temperature resistivity is like this. He knows it follows Bloch-Gruneisen. He can immediately predict what is the resistivity. And not only that, we have actually given a predictive equation that to go from here to here, what is exactly dependence of the room temperature resistivity with the diameter. So that gives you the predictive power. You don't have to measure it. If you have gold or silver or any such, copper, any such nanowires, you know the diameter, you know the resistivity immediately. So it is almost like, you go to the market to buy a spool of wire, and this is what you get. Okay. So now let me come to the thing that, these measurements are all done on a size selected array of wires. It's still not a single wire measurement. So the first single wire nano measurements we did 2009. This may most likely be the first single wire nano measurement of resistivity in the country. And I'm grateful to, at that time we installed our focus ion beam and those facilities. I'm grateful to my friend Phil Priot in Birmingham. He taught us how to do these things and Venkat, who was a PhD student, I sent him there for about a month and he learned how to do it. So this is what he made at the time. This is the nanowire. These are the electrodes connected to them. And we always connect extra electrodes so that if something snaps here, you can make the measurements and you can see that data. The red curve is the measure of the single curve and the blue one is what I get from the measurement of the array. They're almost identical with maybe 5% difference. So it immediately put us faith on our measurement. And let me tell you what has happened due to the impact of this thing. There is a thing called International Roadmap of Semiconductor Industry. It picked up our work as very valuable contribution, saying that this is the way the metal interconnects used in nanoelectronics can be used. So that it was very gratifying for us that what we took up as essentially validation of a physical thing that really got picked up by people. Let me come to the jasusi issue. That is, there are certain issues in the nanowire field you cannot do by bulk measurement, an ensemble measurement. You have to go to really find out what is happening at the single nanowire level. So what I showed in the cartoon is really bringing the theme of what I'm going to say, that I have to find out by experiment on single nanowire, something that I cannot do by otherwise bulk measurement. So this is the experiment we did it on Y-junction carbon nanotube. So this is the Y-junction carbon nanotube. You can see that this is a real close-up image. This is Y, this is one branch, this is one branch, this is one branch. The question came, how are they connected? Is the contact over here semiconducting type, metallic type? And you know that when you have three wires, there are only two ways you can connect them. One is a star connection, other is a delta connection. And this is what our engineering friend told us. And whatever you try, whatever you say, this is true. Either it is star or it is delta. So now this wire was actually not grown by us. It was grown by Professor Appa Rao in Clemson University. I met him in one conference in Hyderabad. And he told me that can you sort it out through your measurements. At that time we started doing optoelectrical measurements, that so we connected the leads to them. This is how it looks like. And she sent her student Deepika Saini to work with us for 3 months under one program, and this experiment was done. So let us see what we get at the end of the day. See, let me now pose the question. Sorry. Let me now pose the question. That, as I said, that you have 3 wires, there are only 2 ways they can connect. Either they have the star connection or you have the delta connection. Now, if you do in the star connection, there is some resistor over here, some resistor over here, now you can immediately see if I measure 1, 2, and 2, 3, 1, 3 is fixed. I have no way I can distinguish 1, 3 separately if I fix the resistance from 1, 2, and 2, 3. But you come to delta, then you have a thing. You have 1 resistor here, 1 resistor here, 1 resistor over here. What it means is that if I measure 1, 2, and 2, 3, 1, 3 is not fixed, is independent. So that is the important thing. That is, so Y junction connection that you are getting, is it dependent like a star or is independent like delta? So we did photoconducting measurements on them. So how did we do it? We actually took the help at the time of Achinta Singha of Bose Institute. He can do focus measurement. So he focused light onto the junction and we measured the resistivity as a function of illumination. There's no change. That means there's no photoconductivity. And what doesn't have a photoconductivity? It is metallic. And you can see it's fairly ohmic. This 1 and 2 resistance doesn't depend on the light shining on it. Same is 1, 3. But the moment, so there's no photo response, these contacts are ohmic. But the moment you go to the contacts 2, 3, you can see the non-ohmicity coming in and there's a photo response. That means that this junction is semiconducting. So now I can immediately decide that the delta type is the connection over here, and the connection really looks like that. Between 1 and 2, you have ohmic contact. Between 1 and 3, you have ohmic contact, but this is semiconducting over here. So at the end, we have sorted it out what is in the contact. So if if you allow me to take the word from Lal Mohan Babu, I'll say it is highly suspicious. But the experiment proved what is correct or not. Very quickly, I'll show you one more example. This has a lot of details. I'll not go into it. Again, these materials we worked on, they have a ferromagnetic order, they have an antiferromagnetic order over here. And at this place, at 0.5 composition, you have both ferromagnetism and antiferromagnetism. So what happens when you make them narrow? The work was really done by Professor Ghosh along with my past students, Professor Hari Srikanth. He's now in a prof in University of Southern Florida in Tampa. Now, what they did is that they very precisely measured the loss, the imaginary part of the high, AC high, and they found that there are 2 temperatures, all right. But then they also measured the entropy, and they found that in this region there is a coexistence of ferromagnetism, ferromagnetic and antiferromagnetic state. But the question immediately came. The question is that, is this phase coexistence, is it due to the ensemble of nanowire who have a distribution of wire diameter, so some were ferromagnetic, some were antiferromagnetic, or is it intrinsic to the nanowire that within one nanowire we have coexisting phases? So the question is a very pertinent question. So we took it up by actually what we call the fluctuation spectroscopy or noise measurement. And this is what we see that, but let us see at the end what we get. And this is an example how precision you have to make your experiment. So what happens is that this is the resistance fluctuation as a function of temperature. And then if you apply magnetic field, you can suppress the magnetic part of the transition, the fluctuation, to this red line. You subtract these two, you get this graph, which is the magnetic part. So the magnetic part of the fluctuation, and you can see that all through there is an enormous noise coming in. So there's a phase coexistence happening. So this work was done on a single nanowire. So now we can say that the phase fluctuation which came, it happened within a single nanowire. So, the doubt that we had that whether it was due to the size ensemble, the size distribution in the ensemble, that you have physically side by side sitting guys which are ferromagnetic and nanowires which are unferromagnetic. But then you should know within a single nanowire you have phase separation. So that is the, I say that there are experiments which you do it in an ensemble, you can find an answer. So that is the strength of this experiment comes in. Now in the last part of my talk, I come to that you can really leverage advantages offered by single nanowire, and you have possibility of observing new phenomena. And when you see new phenomena, it actually takes you a regime of ultra high sensitivity that you don't see in bulk wires or bulk materials and all that. For instance, I give you an example. You go to the market today, and or you sit in Amazon, doesn't matter whether you physically go or not. There are a lot of suppliers of photo detectors in the NIR to visible UV range, silicon or germanium. You can buy them depending on what to buy. The cost may vary. But maybe within few thousand rupees or a few tens of dollars. And like Hamamatsu, or you can get it from various Thor Lab, their agencies. You just order them, and if you are lucky, it will be delivered. But if you look at all those photo detectors, the maximum sensitivity is less than 1 ampere per watt. That means you put 1 watt of light, you get 1 ampere. But you generally don't put 1 ampere watt of light. You say I put 1 microampere watt of light, I'll get 1 microampere coming. That's the sensitivity. But when you made them nanowires, and that I'll be showing you, in the nanowire that we made on germanium single nanowire detectors, the sensitivity that you are getting is 3 times 10 to the power of 7. That is 7 orders more sensitivity, ampere per watt. So even if you put a nanowatt of power on them, I get an enormous amount of current coming out of them. So this has opened up a new vista. We first reported it in 2014. Again, when you do such work, there are a lot of unbelievers. But 14 to 21 is 7 years. The table has turned. Now we have started getting recognition that we have made ultra-sensitive detectors. And at the end, I'll just flash in why they're ultra-sensitive. That is what is the physics, maybe 1 or 2 lines. But let me now turn with a more recent work that we did it in measuring the thermal conductivity of a single germanium nanowire by photothermal spectroscopy. This is a new work that we did, and it was published last year. Now, semiconductor and silicon germanium nanowire has one quality. They actually high electrical conductivity but low thermal conductivity. So they are correct material for thermoelectrics. But measurement of thermal conductivity in a single nanowire is a hell of a lot of problem. Let me tell you why. When you measure thermal conductivity, what do? You just take the wire, clamp at one end, attach a heater at the other end, the open end, and put 2 thermometers, measure the gradient. Now, those of us who have done some part of BSc in Calcutta University, you must have done a lousy experiment. I don't know what is done that. You have to measure the thermal conductivity of a rubber tube. That is a horrible problem. So you have a cranky rubber tube through which hot water has to be thrown as a source of heat, and you have to measure the temperature gradient. Most of the time the results are wrong, but you know at that time when you do BSc honors how to make a wrong result, right? But when you do research, you don't do that. So there's an art you learn when you do physics experiments in your BSc days, but it's a bad experiment you should not follow. But then that is the problem which was solved is the data I'm showing you by a group in Berkeley by Urunava Majumdar. See, what they do is that they take a silicon nanowire, then make it range by nanolithography, then suspend the nanowire, put heaters, one heater becomes thermometer, another becomes heater, etc., etc. So it's a hell of a lot of problems. They pass the heat and then measure the thermal. So that means, and they didn't have a predictive power at the time that if I know the diameter of the material, can I find it thermal conductivity? So we said to do that, is there a non-contact way of measuring thermal conductivity that I don't have to attach a heater or I don't have to measure it, attach a thermometer, can I measure it? So what came to our way is photothermal spectroscopy or using Raman spectroscopy as a thermometer and the laser as a heater. And this is what we have published last year. So this is a fairly recent work. So let me tell you what, we use the Raman line of germanium as a thermometer, and the vary the laser power which is falling on the nanowire at a one spot, which is about maybe little less than a micron, 0.7 micron is the width of the laser line, and use it as the heater. So let me tell you what is the thing. Idea is that I clamp the nanowire over here. It is the way we grow, it is auto clamped. And then I put a laser light over here. And then if I know the temperature over here, I know the temperature gradient. And this is what we do. When you grow the nanowire on a silicon disk, this germanium nanowire, you know, God becomes kind to you. They sometimes show you this kind of things hanging around. Now, if the nanowire is sitting on a base, you cannot measure its thermal conductivity. For it will be ending up measuring the thermal conductivity of the base. But if something is hanging in the air, is a boon. For you know that I can use this single nanowire to measure its thermal conductivity. What I have to do? I have to focus a laser over here and use this temperature shift of the Raman line to measure the temperature gradient. So let us be quantitative. So you can see that this is the Raman spectrometer, this is the laser, this is the beam splitter, mirror, etc., etc. This is the spectrometer. So what I have to do is that I have to measure the temperature shift when the light is falling on it. This is the laser power which you can measure, and this is the contact resistance, and this is the temperature gradient. So if I measure the temperature gradient as a function of Q, I will get a straight line, and this will be the intercept that will give the thermal contact resistance. This is precisely what we did. You can see that nanowire, the laser, this is the laser spot, and which is really illuminating it. There's a blue luminescence from that germanium nanowire, and let us see how we can take it forward. So now what we do is that first we have to make the Raman thermometer. What we did is that we actually put now the nanowire onto a base whose temperature is fixed, and then use the microwatt of Raman power to measure this shift in the Raman line. You can see that the 233 go to 473K. So between 250K to 500K, we can measure the shift in the Raman line as a function of temperature. This was taken with a microwatt of power. So this is the temperature of the base. So this is the real. So if I now use the omega in a nanowire, when I shine the light like this and measure the shift in the omega, I can find out what is the shift in the temperature. So this we did. We use this one. We use this equation with this as a thermometer, measure the Q by a flux meter, and this is what we get. You can see that we focus it at different length from the base, and this is exactly what we apply the power, measure the delta T, and from this we get the slope. We get A is the area of the wire, which you know, length of the wire we know, this is the length, and then kappa is the thermal conductivity. So that we know, so you can really find out what is thermal conductivity as a function of temperature. Now you can see how it depends on the diameter, since it's a data taken on a single nanometer. So you can see from 50 to 100 how it depends, and you can see thermal conductivity increases as the diameter increases. It should be so because the phonons are getting scattered from the surface, and that's why the scattering rate goes as 1 by diameter. So the thermal conductivity is proportional to the scattering time or the lifetime. So that is proportional to the diameter. And then the thermal conductivity consists of two terms. This is the boundary scattering term, and there is a Umklapp process which comes from the phonons, and these theories are known. And so we can see that this really fits this data well. Now what do we get from this? That is, you can see that the dependence of constant and a B by T, and all these constants now we can justify by knowing the physical parameters. We could justify. Now, actually, if you want to be developing of the predictive power, you have to go back to the equation of thermal conductance, where these are the various phonon modes. The summation is over all the phonon modes, and there are two modes, namely the longitudinal mode and two transverse mode. This is called the Callaway formalism. This is a very well-known formalism for thermal conductivity. So when we did that, we actually and got the proper parameters. We could really get, this is the measured data and equation T, that is A by B plus T, and this is what we get from this equation. So they are fairly close by. So now this gives us a predictive power. That's the whole idea. Now if I know the diameter, this is shown as inverse diameter, then I can immediately see now this is a band we have put in. The band comes from the specularity of the reflections of phonons from the surface. So the photons are getting reflected from the surface of the nanowire, and typically they are between 0.1 to 0.3 is the specular reflectivity. So I can immediately see that the ballpark figure in which the thermal conductivity should lie. You know, like for the germanium nanowire, if the diameter is something like 50 nanometer, I know that it will be somewhere between 2 to 3 or maybe 2 to 5. So a ballpark figure I can now give as a predictive power. So that is important, as I told you in the beginning, that the experiment if you do and connect it with a proper theory, you get enormous predicting power, and that is what helps the theory. So now someone comes with a any material, a semiconducting material which is used for this work, and tells me this is the diameter. I said, you don't have to measure it. I can give you a rough value that within maybe plus minus 20% is the thermal conductivity. And for many work, there's a good place to start with. If you need more accurate, you have to do then the actual measurement, which as I told you, it's very difficult. Now let me take the last part. I have about 5-6 minutes left, and so the single nanowire devices, and where from we get very ultra sensitive photo detector made from single nanowire germanium and silicon. So this is the first photo detector that I showed you, the flash tube, and it was published in 2014. And you can see that the photo thing that over a good temperature, photo detection, that's over from 5 to 450 nanometer to about 1000 nanometer. The sensitivity is responsivity is more than 10⁴ ampere per watt. And as I told you, the bulb detector is 1 ampere per watt. So already 4 orders more. Now we worked with the germanium, which has a higher mobility, and this is actually detector looks like, and this is something which we have anchored the wire. These are the real leads, and you can see that we are getting more than 10 to the power 7. It's more like 3 into 10 to the power 7, and they're pretty broad band between 300 to about 1100 nanometer wavelength region. We are getting this particular response. Now you can see that is, when people started work with photo detectors of these nanowires, the 200 nanometer is the diameter, you get responsivity of 0.1 ampere per watt. But of course, it's 10 years back. Now we have 30 nanometer where we are getting a responsivity of 10 to the power 7. And this is one of the highest that has been reported. So but you can see that then that if I reduce the diameter, the responsivity goes up. Then we started thinking why it is so. So let me just tell you physically what happens. You take a solar cell and you have a high quality solar cell. Important point is that in any optical detector, and photo and solar cell indeed is a optical detector, you have to separate out the electrons and holes which are created. Better you separate them out before they recombine, a better detector you have. Now, if you take a PN junction, then there's a built-in field in the PN junction because one side is P, other side is N, and there's a chance transfer that makes the built-in field. For you have to equalize the, equalize the Fermi level. So it is this built-in field that separates out the electron and hole. So this is an axial field. We proposed that there can be, since I don't have a junction over here, it is just a single wire. We propose that there may be a radial field which is separating out electron and hole. And we said why it comes, because if you take a nanowire, its surface is always depleted. That the majority carriers are over here, and due to trap state, the majority carrier are trapped. There are a lot of trapped over here. So how we know how the trap states are working? So we measure the photo gain of these wires as a function of intensity. You see something very interesting. The intensity first goes up when I increase the intensity. And then after that, what happens is that it starts coming down. What happens is that when you have higher intensity, you have a lot of carrier generated. These carriers, fills up the traps. If the traps are filled up, there is no field, radial field to separate the electron and hole, and they are just, they don't have enough electric field. They are left to separate them out, so the PC goes down. So let me just, this was also, we did a calculation by what is called Schrodinger the Poisson-Schrödinger solver, where you classically treat the Poisson equation and use Schrödinger equation to actually sort out the electron energy levels and all that. So what we get, you can see that depending on the band bending or the depletion layer at the surface, there is a radial electric field which is pretty high, and this radial electric field actually determines your the velocity of recombination of the electron and the hole, and that is what increases the optical sensitivity. So now I think I can sum up that, as I said, it was more like a walk the talk, that doing experiments in single nanowires opens a new direction to material science and condensed matter physics. With physics, it brings an application potential, as you said, that the high, extremely high sensitivity detectors. It's challenging and fun, but at times it's very difficult and frustrating too. So, most of the time goes in failed experiments, but when the experiment succeeds, you feel happy. I'm not sure whether I can convey to you what I wanted to say or what is the experiment, but I thought I tried to convey at least my excitations to you, and thank you very much for your attention. Should I stop screen sharing?
Yes, sir. Thank you very much for this nice presentation. Very insightful lecture, and I believe the participants have gained immense idea in this field. And now the forum is open for discussion. In case if you have any query to Professor Raychaudhuri, I believe there will be lots of query. So what is the Purva? Please tell me whether they will whether they'll write in the chat box or they will be they can ask the question directly.
No, I will request the audience, if you have any question to Professor Arup Kumar Choudhury, please write down in the chat box, and we will take 2-3 questions because of the tight time schedule. So please. Is there any question from anyone?
One question from my end. Industrial relevance, particularly in the field of biomedical devices and instruments, if you can please give some idea based on this type of materials.
Hello, sir.
I'm unmuted now. Yeah.
Okay.
So see what happens, what I didn't show you, extremely high sensitivity detectors in the biothing can be made from these nanowires. And they have been made, particularly semiconductor nanowires. I didn't touch on it. And there's actually a very good group in Berkeley, Professor, I forget his name, the Chinese guy, who does enormous work on this field. And they can detect even at the level of single biomolecules now. That, like whether it's the level of single DNA, not single DNA, but I should say at the level of, maybe few nanometers clusters of biomolecules they can detect. So there's enormous application in the field. And, actually it has to be, one has to put this thing inside some kind of a channel through which you can put the biomolecules. So there's a lot of lithography work the one has to undertake, but it's a very profitable field.
Okay. Okay, thank you, sir.
Thank you.
So any other question from participants? If not, then let us, any question?
No, ma'am. I didn't see any question here, so we can.
Okay, so let us have a big hand to Professor Raychaudhuri for this excellent lecture. And if any query rises in later time also, I will
Yeah,
request
no
the
problem.
participant to send a message to sir. And I hope sir will be able to guide you in that direction.
Thank you.
Thank you. Thank you, sir. Thank you
Thank
very
you.
much.
Thank you.
Momika
Now,
ma'am,
we are having lunch break.
no, no, sir. We have now talked from Professor Bornali Ghosh. So,
Oh, yes.
Momika ma'am, can you please? Professor Ghosh is already here. Welcome, ma'am.
Great.
Hello.
But,
Hello, good afternoon.
Good afternoon.
good afternoon, madam.
Good afternoon.
So,
Can you see me? Yeah.
Yeah.
Yes, ma'am.
Yeah.
Our the second lecture that will be delivered by Professor Dr. Bornali Ghosh. Madam is now working as a scientist, professor in the Department of Condensed Matter Physics and Material Science, and head of the Department of Technical Research Facility Program. She is a member of Indian Physics Association. She got PhD degree in Physics Award in 1998 and got Research Award in Women Scientist Program in 2003 and 2008 from Department of Science and Technology, Government of India. She, along with her research group, while focusing on basic physics, is also exploring application-oriented and technology-driven basic research in material sciences as well as nanoscience and technology. She works as an activity leader in establishing an application-inspired innovation and technology-related work which has good impact in the society, healthcare and food care sector, and environmental protection through innovative material design. Her group works with a good number of PhD students, postdoctoral fellow, and young scientists. She and her group have filed a number of patents based on their innovation and has published good number of research papers in reputed international journal with citation globally. So today's talk, perovskite halides as a new platform for sensors. So with this, I will request Madam for today's lecture, and we are from the on behalf of the organizer, we are very much thankful to you for your time that you have given to us, and you have agreed for this invited talk. So over to you, Madam.
So thank you for this nice introduction. And first of all, I would, am I audible properly?
Yes, Madam.
Yeah. So first of all, I would like to thank Professor Bimal Sarkar and you for inviting me in this prestigious lecture. So shall I share my screen?
Yes, I think it is allowed.
Can you see?
Yes.
Yeah. How to minimize the top A?
You can make the screen a full screen mode.
Yeah, I am given. So I am Bornali Ghosh from SN Bose Center, already introduced. First of all, I like to thank all of you and the audience. Before I come to my talk, I would like to thank Professor Rai Chaudhuri. I am working with Professor Rai Chaudhuri's group. We are working for a long time, and we are mainly working on nanowires and devices. And along with the nanowire devices, we are also working with some thin films as well as bulk and single crystals also. So as Professor Rai Chaudhuri has described detail in the physical measurements on single nanowires as well as ensemble nanowires. So I am not going to the detail of all these things because it will be overlap of all these things. So we decided that I will just give an example before coming to my main lecture. I will give an example about what are the types of work we are doing in the lab, how we are growing, especially for the students, how we are growing the nanowires and all, and how we are doing some other type of works in the lab. So we are mainly focusing on the 1D systems, metals, semiconductors, complex oxide, halides, all these things. So we follow several routes like wet chemistry and physical vapor depositions. Wet chemistry means this is the autoclave, this hydrothermal reaction. So I will come show some of the detailed SEM images of the different nanowires grown by different methods from our group. So these are the template assisted nanowires grown in the AAO template that Professor Raychaudhuri has explained in detail. This is the electrodeposited metals, and this is the copper TCNQ, that is physical vapor deposition method. These are silicon, tungsten oxide, all these nanowires. These are grown by chemical etching, and this tungsten oxide is grown by pulsed laser deposition. And these are the physical perovskite halides. I'll be talking mainly on this perovskite halide system. And we are also working on the complex oxides. This grown by hydrothermal and single nanometer measurements. My student has submitted a thesis on this work. So these are the various types of nanowires we are growing in the lab. So first, I would like to say that the science and application of electronic materials. So how we engineer properties of materials. So first of all, it is ability to grow defect-free pure material with proper composition and stoichiometry. Then ability to modify the properties of electronic materials in a controlled and reproducible way, that is engineered the properties of material by a number of enabling tools and stimulus. And then do the theory and simulation for understanding the underlying phenomena. And materials can be any type, elemental, binary, or complex. So how we do the modification of properties? So it can be done by controlling charge carrier concentration, either by substitution or light, controlled by crystal structure. It can be controlled by strain. It can be controlled by magnetic field also. And it can be controlled by temperature and can be done by controlling size. So first I will come to the how we control the by size. So is a strain. So we know that if a substrate has lattice spacing is larger than the thin film, it will be growing. So it will have a compressive strain. And if the substrate lattice spacing is smaller than the film you will be growing, then there will be tensile strain. So these two kinds of strain you can grow. So first of all, you also have to know that if the thin film thickness is very less, then only you can do this or see all these strains. Otherwise, it will be strain relaxed. So if the film is strained or compressive or tensile strain, there will be differences in the TC. This is metal insulator transition temperature may be changed. So there is a very old work from Professor Raychaudhuri's group. It has been shown then how the TC can be tuned by tuning the strain. Now let us see that this binary oxide nanowires, we are going by pulse laser deposition. Here we took substrate of different type. This work is done by Shomik. He has already finished his PhD. He is looking for his postdoctoral work. So it has been grown on two different substrates of different lattice mismatch. So one is silicon oxide, another one is SrTiO3. So when we grow on silicon oxide by the same deposition condition, using the same material, same target, so we see by PLD we got the nanocrystalline film. And when we grow on the SRTYOT substrate, the single crystalline substrate, it shows an oriented with needle-like structure. So if we apply light, does the film morphology affect the photoresponse behavior? The answer is yes. We saw that in case of nanocrystalline film, it is showing on-off behavior, whereas for the oriented film with needle-like structure, it shows persistent photocurrent. So the basic physics is the photoconductivity kinetics. This rise and decay depends on the defect states and their passivation. The film morphology tunes that leading to the change in the response, although the chemistry of the material does not change. So now we see how we can change by substitution. So this, as we know, this is a very old material, lanthanum manganite system. It is insulating antiferromagnetic. There's from this curve, rho versus T curve, you can see it is showing insulating behavior. If we dope with calcium, then it will show the metal insulator transition. So by doping, we can tune the metal insulator transition temperature. Now let us see if we put hydrostatic pressure on a calcium doped lanthanum manganite system. What will happen? We have seen that initially it is showing ferromagnetic insulating behavior. This ash color curve is the original curve before putting pressure at zero pressure. If we apply pressure on it, then you see and do the resistivity measurement, you see that there is a change in the resistivity behavior. And around 1.3 GPa, you see it is showing the ferromagnetic metallic behavior. It's nice metal insulator transition. So by under hydrostatic pressure also, you can tune the property. So let us see how we can tune the property by the doing the size reduction. So we have taken lanthanum manganite, as I have told, it is orthorhombic antiferromagnetic, it is bulk system. Now if we reduce the size, it is then we saw around less than 50 nanometer nanoparticles, so rhombohedral and ferromagnetic structure. So let us see, we have done the detailed neutron diffraction experiment. It has been done on D20 beamline at ILL Grenoble, France. So we have seen this is the antiferromagnetic peak, and it is showing nice antiferromagnetic behavior from the neutron diffraction measurement. When we reduce the size, then we saw this in the nanoparticle system. This antiferromagnetic peak is dissolved, and we saw this is a ferromagnetic behavior it is showing. So we have analyzes the data by Rietveld refinement in detail. My student, and this is my work. So, sorry. So I have done this work when I was doing the postdoctoral, when I was doing the visiting scientist or something like that. So I have seen that this is the magnetic moment behavior, and it is showing the antiferromagnetic transition around 120. But in case of a lanthanum magnetic system, it is showing nice ferromagnetic transition around maybe 250 here. So by size reduction also you can change the property, physical property. So physical property of the material can be tuned or engineered by a number of routes without changing the chemistry. So let us see how we grow the material in our lab. So we grow by template assisted growth method that Professor Chedire has already shown. So I am not going into detail of this. We are also doing by template free growth of metal nanowires. This is a chemical etching. This is the hydrothermal method in the autoclave. So this is complex oxide nanowire. This is vertically aligned TiO2 nanowire grown on FTO. So these are different kind of nanowires our students are growing in the lab. So we are doing the physical vapor deposition method also to do the measurement. to do the growth. So this is the evaporation technique. Professor Raichodhuri's group has done this copper TCNQ work. So Rabia has done this work. And we are also growing by PLD the fine vertically aligned nanowire by controlling laser energy, substrate temperature, background gas pressure, target substrate distance, and the rate of deposition. So all these parameters we have control, and it took long time to us to standardize, because all of us know that pulse laser deposition is well known for thin film growth, but it can also be used for nanowire growth, that we have shown first. So there are two methods of nanowire growth in PLD. One, we have used the top-down approach, is the control of growth parameters. We have grown the vertically aligned nanowire, and another one is bottom-up approach. What we do, we have grown the nanowire on the substrate and do the nano patterning and make the in-plane nanowire. So these are the vertically aligned dense forest of nanowires. This Dr. Ankita Ghatak, she is a scientist D, and she was associated with me at our center. Now she has joined with Professor Raichodhuri as CDCRI, and Shomik also has done this work. So this is a thin film grown on tungsten oxide, thin film grown on silicon. We do nanolithography, and we by FIB. By ion milling, we have cut from both sides, and we can grow the nanowire. So whatever size, diameter you want, you can do. This is 80 nanometer, 45, 35, all this nanometer. So how we do single nanowire measurements that Professor Raichodhuri has shown in detail. So this is a single nanowire. So we are using in the Helios dual beam system in our laboratory. So how to make single nanowire devices? So we do the prefabricated aluminum chroming electrode in the silicon nanowire, and then we put a drop of dispersion containing nanowire in this portion. So we can do the interconnection made by platinum deposited using E-beam assisted lithography. And this is a zoom image of this here. You can see the nanowire. Nanowire you cannot see. This is a big contact pairs. Now, if you again zoom it, you can see the nanowire. This is 50 nanometer complex oxide nanowire done by Subarna. So Subarna has done a lot of effort, and it is very much challenging work. Every day she used to cry that it is nanowire is burning. It is not working properly. Finally, we could make contact on nanowire. This is a 50 nanometer complex oxide nanowire, and she has done these measurements, and this work was done along with Professor Raichodhuri's group, and we have done noise measurement, and he has explained that how we have done the physical measurement, but it was not told that along with the ensemble measurement with the magnetocaloric, we have also done extensive structural work with the ensemble of nanowires. I will not go to the details. We are doing synchrotron and neutron diffraction study to know how the phase separation has been can be explained using these nanowires. So I am just mentioning this one as I am also not touching in this part. So we are also doing interface study by doing cross-sectional TM study by using conventional as well as ion beam lithography method. So how to make TM cross-section specimen? Different steps is needed, and which is very important part and challenging. So all of us, we know this is the TEM grid. Normally we do the TEM image. This is the OmniProbe grid. Here we have to mount the cross-sectional this part specimen. So this is the vertically aligned nanowire with the top view. First, we do the platinum deposition on top of it, then cut from both sides by ion milling. This is top is the platinum. This is for holding the specimen after cutting. This lip top is done by oiling with the platinum in this part, So this is the OmniProbe. It is just picking up the specimen. and then it is mounted in the grid in this portion. So this is the mounted over here. Then after that, you have to cut it from here. So this is the zoom view. Here, this is the substrate, and these are the nanowires. So final thinning, it is less than 100 nanometer. After that, you can take it under TEM and you can do the analysis. So Ankita and Shomik has done this WO3 nanowire work, and we could publish it. This is a first report, and it is very much well seen by the people. So this is the aligned nanowire cross-section part, and this is the substrate. From here, we have analyzed how the growth mechanism can be analyzed from this data. So I am not going to the detail. So another one is work is done by Chandon along with Ankita. He has submitted his thesis and going for postdoc. Now let us see. This is ZNO nanowire done by chemical etching. On top of that, by hydrothermal growth, he has deposited ZNO nanowire. So this is the heterostructure of these two material. So now we wanted to understand the microstructure and composition study. So we have again done the cross-section and do the analysis and find out how the compositions are distributed, and some other measurements also we have done. So let us come to the main part of my talk. So before coming to that, I would like to mention that Professor Raychaudhuri wanted to make application-inspired innovation and technology center by sponsor, which sponsor can be done by DST. So the one project was proposed to establish an innovation incubator center within the Bose Center that would build harnessable science and technology platform. So we are doing basic physics. We didn't have that time, no idea around 2016. We have no idea how to do technology-driven work. So we just get inspired from him and started working. So now this is most deliverable, and all these things are the healthcare mission. This integration with the major national program. How can be done? This is healthcare mission, Digital India, Make in India, National Food Security Mission. And here this project finally came at our center. This is a very big project, and he was a nodal officer, and we, some faculties were the activity leader, and we started working. So, and also we have to make the output relevant to the societal needs in the addition to the value in commercial space. So our technical research center formed in our center. So our mool mantra was making us effective in the innovation space. So we started focusing on healthcare sector, diagnostics and emergency invasive techniques, environmental related issue, and food security. So we aim to investigate some of the important science as well as application potential of perovskite halides by tuning various parameters to make an attempt towards translational research utilizing novel application potentials of them. So this is one of the perovskite material is one of the emerging research areas of material science in recent days. Abhishek has done his full thesis on this work, and he will be submitting soon. And he has done a number of publication and number of patents related to this work. So this structure is actually a BX3 type structure. Here, this material has very high carrier mobility optical gain, which allows them to be used for various optoelectronic application. And important properties, it has a very long diffusion length, high carrier mobility, and band gap tunability. So state of the art of this material, this is a perovskite solar cell, and mainly people are working on this type of work. So till date, it has been achieved 27% conversion efficiency, and PLED is 20%. So we thought, can we think around the perovskite sensor? So no one has done this kind of work that time. So we are the first, we have done this sensor kind of work in this system. So we thought that can we tune charge carriers and crystallography structure using different external stimulus like light, gas, or radiation. So whether such tuning can tailor the physical properties leading to different novel application potential. So this perovskite halides ABXC type structure that I have already told. So we have worked with different cations along with lead. This is the B cation. Lead is a B side cation, and we have also worked with different anions, this bromine and iodine. So by all these three types of combination, we could make this MAPI, we call CH3 NH3, PbI3, methyl ammonium lead iodide, we call it MAPI, and now onwards, this is short form. This structure is tetragonal. This one is formamidinium lead iodide. This is PAPI, we are calling. This is trigonal. Another one is CH10 is here in place of iodine, we put bromine. So this is the cubic. So here we have changed the anion in two cases, and here we have changed the cation. So let us see how this family of this perovskite halide works. So this family of perovskite halides, can it be used as sensor? So we have engineered here the halide perovskite family in such a way so that it can be used as ammonia gas sensor, broadband photodetector, which can work up to UV2 NIR and gamma ray detector, either by tuning structure or as well as charge carrier. The same class of material, beauty of this is the same class of material respond to different external stimuli, leading to different application potentials. So one of the most interesting thing in this family of perovskite halides that it has been grown on paper innovatively, making perovskite sensor devices compatible with the paper electronics. The major challenges in this work is exploring areas apart from solar cell or photovoltaics, because people are doing only this kind of work mainly. So we at the first time we thought whether it can be used as sensor. So standardizing the growth and good quality films, highly oriented crystals also, and fabrication of devices, that is also the main challenge using paper-based electronics. So we have done characterize the material grown this on paper. So this is the MAPI material grown on paper. This peak is coming from paper. This is the bare paper substrate. This is fiber-like, and this after growing it looks rod-like surface morphology. This is tetragonal structure. So we have prepared the other materials also. These are the tetragonal structures for MAPI I have already told. This is MAPB, it is cubic. This peak is coming from paper, and this is trigonal. So the material, different material of the lead family shows different kind of structure. And this family of perovskite halides, let us see how it can be used as a new generation solid state room temperature ammonia gas sensor. The perovskite halides ammonia gas sensor, why we have thought about it? Because I will show how why the necessity of hazardous gas sensor is required. Solid state sensor of different sensitivity for different usage I will be discussing, and what is the basic physics behind the sensing I will discuss. So first of all, I see why we are interested in this kind of sensor, ammonia sensor work. The ammonia is one of the most hazardous environmental pollutant, and it is fatal to human health beyond 25 to 30 ppm. And detection of trace level ammonia is very much essential in areas like agricultural, fertilizer industries, food, beverage, and cold storage industries, refrigeration, and medical diagnosis. It can be used as marker for renal disease, chronic kidney disease, and can be used to check the efficacy of the dialysis. So we can think this can be used as application areas. You can if you do some this sensor kind of work, you can help in these areas. So hence, we thought that making of sensor for detection of ammonia gas via a simple, robust, and more inexpensive way. As that time we are thinking about the technology. So we thought it should be an inexpensive way, has an immense application interest as a cheap vehicle to mitigate public health hazard and to detect early sign of organic decays in storage, different storage facilities. So, but the sensor, there are several sensors. You can say that there are several sensors, but there are different issues. Though there are several materials and nanostructures are being used as sensor for environmental pollutant detection, the major factors and desirable features for usage of this gas sensor in real field application with proper technology embedded with it are detection limit problem, selectivity problem, working temperature problem. Most of them are working at high temperature. And cost effectiveness problem, and the fabrication technique also. It should be very much easy to fabricate. So believe me, we could grow the perovskite halide ammonia sensor on paper that visually it can sense. It's a very new technique, color change type, and it can sense up to 10 ppm. And the other one, we could do electrical measurement, we can sense less than 1 ppm. By using paper electronics. First, I will discuss about this one. This is grown on piece of paper, very cheap, cost effective, and can be used as disposable basis, and it is workable at room temperature. So what is the state of the art of this? The paper based, it is a very fast response ammonia sensor, visual sensor. We could, the patent, we have patented this work and it has been granted. And the proof of the concept is established and patent has been granted and prototype is ready. So this work first report of from our group in the scientific report, and the perovskite sensor paper. This is the real sensor paper photograph, and under ammonia the color is changing to yellow. So this is very easy to detect ammonia at workplaces. So main features is very fast response, disposable, and it is like a pH paper. So we know that good sensors should have very high selectivity, sensitivity, and it can be worked at unheated operation. At least it should not be high temperature operation and cost effective. Our visual sensor is high sensitivity, high 10 ppm selectivity, very good selectivity. It is humidity insensitive and workable at room temperature. It is paper based and very quick response, 5 seconds, portable and standalone and disposable. So we have plotted the response time with the concentration of ammonia gas, and we have seen when our concentration is 10 ppm, then it is sensing around 12 seconds. As we go on increasing the concentration, say around 30 ppm or 25 ppm, then we saw it is very quickly response. It is around 4 to 5 seconds. So with increase of ammonia concentration, the response time quickly decreases, and at concentration 20 to 25 ppm, when it approaches the danger level, I told that 20-25 it is fatal to human health. So the sensor that time quickly turns its color within 4 to 5 seconds and gives when you apply ammonia, and so within 4 to 5 seconds the color is changing. So this gives us a visual warning. So we have checked whether the other compositions also sensing as well. So we saw that we have already told about the structure. We have seen the surface morphology, but the surface morphologies are different as well as like the structure. MAPI is a rod-like, this is cubic, and these are the fiber-like structure. MAPI. So let us see visual color change, how the family reacts in ammonia exposure. So we have, I told that we have changes the cation anion. This organ, and this here we have taken iodine. So this gives MAPI. If you change bromine, if you make MAPB, then it is color is orange color, original pristine color of the material. After growing, and in ammonia it is white, colorless. And here we thought we will change the cation. So we change the cation part. then you go puppy, and again the color is black. All these are real samples grown on paper, and in ammonia it shows yellow color. So visual response is quantitatively independent under alteration of cations and anions. Also, it is independent of the structure and surface morphology. So these are the materials after growing and after ammonia exposure. So I just jot down all these things, colors, and limit of detection. MAPI is very fast, is good, 10 ppm, but MAPB is 50 ppm. It is MAPI is 80 ppm. A response time is 10 seconds. It is 2 to 3 minutes, and it is greater than 4 minutes. So let us see our this setup. This is custom-made setup Abhishek established in the lab. This is the gas inlet. So this is the mixing chamber. Here we mix the gases. This is the measurement chamber. We put the sample over here. This is a mass flow controller unit. This is a source meter. This is the mass flow control. This is source meter, and through this we measure data record has been done through the computer. So now we thought we could go up to 10 ppm visually. Let us say, can we make much more sensitive this solid state sensor? So it can be used for the medical diagnosis, because there we need very less 100 ppb or this highly sensitive gas sensor is required. And it can it be read out device with cloud compatibility. So for thinking this way, so we this is the material, and we just deposited electrodes by depositing evaporation method. These are the metal electrodes, and this is a real sample, and we did pressure contact measurement within the on the sample. So then we saw. We put a scale. This is the visual up to visual 10 ppm color change, and here we see that there is no color change. You cannot see, but you can do the electrical measurement, and you can see this current noise limited detectivity is 10 pp at room temperature. So sensor based on paper electronics detect ammonia much before the color change effect occurs around 0.1 ppm. So we have done the measurement at different ppm level, 20 ppm, 2 ppm, 4, 6, up to 10, and we saw the current is increasing. So current response, it shows current response. So we have plotted the sensitivity with ammonia concentration for different materials. This is MAPI, it is highly sensitive, then it is MAPB, and this is the PAPI. So this is a material, it is flexible, and we have also flexibility check and did the measurement doing different bending. We saw that properties not changing, and data sensitivities was not changing much, only 3 to 4%. Now we also wanted to check the other parameters, whether it is sensitive. It is very much stable. We have checked 150 days. That time we put this gap with, but we have seen that up to 6 months also it is staying very nicely if you put in the desiccator. It is also very much selective. It is selective to ammonia only. We have checked for many other gases. It is also stable in other humidity. It has been checked. So I jot down all these materials. This is MAPI scale. This is MAPB scale. Then up to this is visual 50 ppm. Below that it goes up to 300 ppb electrically measurement. And this is PAPI. I told it is very less. Yeah, it is 80 ppm. And after that it could do electrical measurement. It goes up to 500. So different crystal structure, different morphology, different electronic structure, but qualitative nature of the sensing remains the same. So let us see what is the physics behind it. So this is we have taken the XRD or the pristine MAPI grown on paper. So this is the X-ray done on it, and after that we fully exposed this material, and color is yellow. We took the XRD, and this XRD is very much similar to PBI2, and this is PBI2 we have done with this PBI2 powder, and color is also very much similar. So the MAPI decomposes to P/2 in ammonia. We just thought that it must be converted into PbI2. So we thought there should be much more. Another one, we have also, sorry. PbI2. Oh, okay. It is not going to another one. Okay. So we thought that we are still not happy. We thought we should get some more evidences. So we do electrical transport, and we saw this is the MAPI, original MAPI pristine thing, and we saw the electrical conductivity increases. This is for MAPB in ammonia, and it is PbI2. The PbI2 is, we know that it is ionic conductor, so conductivity increases. We also done the spectroscopy measurement. We thought this is MAPI, and we have seen this MAPI in ammonia. It is very much merging with PbI2. So we can conclude that it is converted to corresponding lead halide. It is for MAPI. This is lead halide yellow, and for MAPB it is PbBr2, and for other things also. So I did not put all the data together. Still, I will show this data we have done for other materials. MAPB, evidence of spectroscopy we have seen, and also electrical conductivity transport measurement also we have done in PAPI and MAPB. So we could conclude. And another one I want to say that we have done some simulation kind of work. Shoikad has done this work. He is doing PhD. So he has done the molecular dynamics simulation, and we have seen that simulation shows there is a temperature rise during reaction, and so we are concluding that hence the reaction is exothermic. I am not going to the detail of the this analysis. So we, based on the adsorption ammonia molecules, this chemical reaction converts them to the corresponding lead halides, which are ionic conductors. We have seen all this ionic conduct, PbI2, PbBr2, all these things, and this is increases the conductivity and enhancing their sensitivity under ammonia gas environment. So we can conclude that thus origin of both visual color change as well as electrical conductivity change under ammonia exposure is due to decomposition to respective lead halides from the family of perovskite halide, and it is corroborated with simulation results. So we established that response by lead halide perovskite family towards ammonia gas is qualitatively independent of surface morphology, crystal structure, substitution or alteration of cations and anions. Thus, the origin of both visual color change and electrical conductivity change and ammonia exposure. This work shows that lead-based perovskite halide family would provide a general platform for room temperature unheated solid-state ammonia sensor, which is compatible with low-power paper electronics. So we have made some lab-based prototypes. This is the we told it ammonia watch. This is the ammo watch. This black color is the material over here. You can change the paper once we use. When you walk in the area where the ammonia exposure may work, the worker may wear it, and if they see color is changing, they can leave the place, so they can save their life. And also you can use as a paper roll. You can take the piece of paper and use like a litmus paper or pH paper. You can put it in the room wall, and if you see the color is changing, this is material and the color is changing, you can leave the place safely. So this patent has been granted recently. Now I will say that this is also new work. Perovskite halides as broadband photodetector in the paper. A study was done on operative properties of mixed cation. We have done in the mixed cation. We saw that it is very much stable and are also showing good results. So it is also done by using paper electronics. These issues, existing perovskite photodetectors are the stable response, long-term stability, very high bias people are using, greater than 10 volt, and very high optical intensity. So our approach is a compositional tuning and choice of substrates. So we have used paper. So what is the novelty of our work? We have seen NS spectra's response in UV NIR region compared to single cation MAPI and FAPI photodetectors due to mixed cation, and paper-based flexible broadband photodetector also we could make, and operable at very low optical intensity, 0.1 microwatt centimeter square, and very low bias, 1 volt. So this is the current time plot. This is, we see this MAPI and this is FAPI. This is FAPI, this is MAPI, and this mixed cation shows very good response. So the essentiality of the mixed cation is that it combines high response by MAPI and stability by FAPI. It has been checked by several experiments. So this is directly correlated with the absorbance with the material we have seen from the photocurrent and the absorption data. And we have plotted the responsivity with the wavelength, and we saw that in the UV region, it is very enhanced response, more than 1 order in the UV region. Now, I will come to the last part of my talk. This is we have also developed a highly radiation resistant gamma ray detector using organic perovskite halide. This work has been done on the single crystal of FAPI. So it is very what I can tell, not easily, but still we can say very cheap approach. This is a solution grown single crystal. It's a very big crystal, 4 millimeter, highly oriented crystal. We have taken the XRD and all. So from the absorbance and the normalized PL data, it is quite clear there is no defects in this one. So we can say easily that our sample material grown is very good quality, defect free. So what are the issues? Issues with the existing now available sensor detectors are this complicated detection techniques. People are using energy resolution method, and it is operating temperature is very low temperature has to be used, 77K, and very high manufacturing cost because they has to prepare the ultra high pure crystals. So our approach is our important novelty of this work is room temperature operation, simple and quick direct detection using electrical readout like our ammonia sensor, and high radiation sustainability and also good mobility lifetime product, and the low cost simple solution process synthesis. So with this work we have done in collaboration with Professor Abhijit Shah at UGC DAE CSR Kolkata Center. This is we have used their irradiation source cobalt-60, and strength is 3.7 kilocurie, and strength during experiment was 1 kilocurie, and half-life was 5.26 years, and average energy of the emitted gamma photon was 1.25 MeV. And gamma ray source was inside with a high protective lead sheet. Here these are the lead sheets, and inside this the gamma source. So direct detection of gamma ray using the electrical readout method by using highly oriented FAPI crystal. How we have done it? So we have plotted, we have seen when we apply, but when we impinge the gamma ray on our crystal with cobalt-60 gamma source with 1 kilocurie activity. This is the first one, this is a 10 volt. So we saw this, there is a increase in the current. As we go on increasing the voltage, current is increasing. So it is sensing, detector is sensing the gamma ray. So we can detect gamma ray easily by electrical measurement. So detector current has been plotted with the voltage. It is showing that with the voltage it is increasing. So it is very easily one can detect at room temperature gamma ray using this FAPI crystal, and it is also very stable. So also we have checked whether our detector is good or not. So we have, this is a mobility lifetime product. It is generally detector, it's characterized with the qualities characterized with this mobility lifetime product, which is a fundamental figure of merit of any redirection detector. So what we did, we have done from the IV card, we have calculated the mobility product, and our mobility product is this, and it is compatible with the existing detectors. Somewhat we can say it is good also. So we had we didn't patented this work, but we have to patent it. Let us summing up this work. The investigation of gas sensitive property by family of lead halide perovskite we have done, and this is actually happening because of the decomposition towards lead halide leading towards high sensitive gas detection. And investigation of optoelectric properties of mixed cation perovskite halide in a broadband UV visible in 300 to 900 nanometer region using paper electronics. Effects of cation engineering makes a stable broadband optical detector, and direct detection of hard radiation gamma ray detector using high oriented crystal of perovskite halide by electrical readout. So beauty of these, all these detectors are, all three detectors works at room temperature. So before coming to the end, I would like to share, I would like to take the opportunity, what are the other types of translation and research is going on in our lab, students are doing. So first of all, just I will say that Chandan has done the material, what he has submitted the thesis, this heterojunction of two material. This is a PN junction material, or this is a silicon grown on silicon, nanowire growth. So we have seen that most of the detectors, sensor detector, they have limitation. I have already discussed, and the detection capability is below 10 ppm, and also selectivity limitation and elevated operation temperature. The heterojunction of two material, we have seen that forming PN junction array, that leads to detection capability at least down to 0.5 ppm with a noise limited resolution down to 10 ppm at room temperature. It has very low projected cost and easy readout with remote access through Wi-Fi and wireless technology. So this is a response card. So we have filed a patent and replied the FEI report, and it has not yet come, and the answer. So, and we could publish a paper also. Nitric oxide, why we are interested? Because it is also hazardous to human health if inhaled above 25 ppm, and it may cause depletion in ozone layer by converting NO2 and O2, and exhaled ammonia and NO can be used as a marker for asthma and chronic obstructive pulmonary disease, COPD. And another work, this Ankita, Shubhamita, and Shoili was doing this a technique to regenerate the perovskite phase of BATI thin film, because Shubhamita, she is associated with Professor Rai Chaudhuri. She has submitted a thesis recently. She used to work on BATI film and used to grow by PLD. While growing, they are facing a problem because it is not giving the proper stoichiometry. So what they did, it has been done, the cross-sectional lamella preparation, it has been done, and detail X-ray and XPS, all these things has been done in detail. And it was found that the thin film grown, it is titanium rich, because barium, we know that very much volatile, and as we are growing BHA at high temperature, so barium is coming out. So this stoichiometry disproportion is there. So restoration, how can be done of perovskite phase on the top layer of thin BTO film? By plasma treatment, we have done plasma treatment and annealing. What we did, this is the BATI thin film grown on PTSI. So it has been found that TiO2 enriched surface. So we do argon plasma, and after argon plasma etching, the surface become rough, and it is also non-stoichiometric still with BTO film. Now what we do, we reconstructed this the perovskite phase by putting extra barium on top of it and then anneal. So we have just patented this work also, because it is a very good method to restore the perovskite as well as the phenolitic property, and the patent has been granted recently. And we have found that initially the X-ray shows the non-perovskite phases as well as TiO2 phases. After this reconstructing the film surface, we saw all these perovskite phases are there. Initially it was 63%, now it is 100%. Also, there is an increment of 2.2 times and from this in case of this data, dielectric constant data, and also increase in the remnant polarization is about 10 times. So there is improvement of this property also, and this is a granted patent. Another, this is the final thing I am showing. This is PZT nanowire based this nanowires we have used. This is when we that because we know that we have having some waste energy, it can be used as but it can be used for some other good work. So we could make nano generator based on PZT nanowires. PZT nanowires were grown by Yonkita, Naomi, and Shubhamita help there for measurements. So PZT nanowires, needle-like nanowire they have made, and we make a piezo cell. And using this nanowire, we could generate by applying by tapping on these things and make it. First of all, we make a chip kind thing, and on top of that, if we tap it, then we can, it is converted this waste energy in the electrical energy or output voltage. It is around 8 volt and power is 250 microwatt, and one capacitor can be charged within 40 seconds. And we could make we could make a smart shoe. This is Sneomoi's leg, and she is wearing the shoes, and while walking she is charging the mobile. So device can be charged by direct charging, walking, jogging, or cycling, or exercising, and it can be charged by indirect charging also. If we attach a battery inside the shoe, it will charge battery during motion and can be used in the targeted device. So this patent has been recently granted around 2020. So we got so many granted patents. Earlier, we didn't have any idea how to write patents and all, how to get this, how to do translation research. We are very much thankful to Professor Raychaudhuri. He got this kind of project, and he inspired us to do this kind of work. So we could do this kind of work since 2017 onwards. We are doing this kind of work. So some of the works we are still going on for commercialization. Commercialization is not yet done. The testing and validation has to do techno-market survey for such product, design and specification fixing based on survey. So all this work I have to do, build a portfolio for marketing, link up with device manufacturers, start marketing products, initiate work on knowledge and resource hub and incubator process, and establishment of commercialization through incubator program. So all these major works we have to do. Some of the works we have already done, and some are we are still doing. So finally, I would like to thank to all our group, all my group members, thank to our technical staffs, and also thank DST for funding. And I have used several experimental facilities for different work, so I should thank them. I have used our central equipment facility at our center. The Professor Raychaudhuri had made a technical cell for different instrumental facility are there. I was there as a in charge in these things. I have also used UGC, CSIR equipment facilities, different places, neutron beamline, India and abroad. So finally, I thank to my group. This is my present group. I am also thankful to my girls. I am very much proud of them. Being a woman, so I should also thank to them. Some of them have already submitted their thesis. Some have gone to abroad for postdoc. Some are still doing PhD. Some have submitted. So let us thank you to all for your kind attention.
Thank you, Madam. Thank you very much for this excellent discussion and the work that you have carried out at S.N. Bosch National Center Basic Science. Really, really very good.
Thank
so
you.
I know that many of the participants have questioned to you. The forum is open for discussion now. So participants, you can write your question in chat box or you can raise your hand so that I can unmute you and you can discuss with Madam with more details.
I didn't see any question till now in the chat box.
Madam, recently COVID-19 detection from S.N. Bosch, I think sir already discussed few topics. A chip was developed, right?
Yeah.
That was from your institute, right?
Yeah.
We read that in newspaper.
Read
that in newspaper.
Yeah. And our students are working here several areas because we are in the translational research, we are new. So we are trying to do our best to do this work, this kind of work, along with our basic research also.
Now, what is the status of that chip now, Madam? Is it clinical trial already done?
No,
not yet. Okay. Okay. So anyway, we are just before the lunch break.
Yeah.
So
all are hungry.
So I think the students and the participants, if you have any query that comes later in your mind, please write to Madam. Madam will be happy to give you the answer.
Okay. I'll be happy. Yeah.
Thank you, Madam. Thank you.
Thanks a lot.
Thank you.
Yeah.
Okay, so let me thank Professor Barnali Ghosh, Professor Arup Kumar Rai Choudhury, and our respective session chair, Professor Jitendra Kumar Pandey and Professor Moumita Mukherjee for this wonderful two session. Thank you, sir. Thank you, ma'am. And just before the lunch, I want to make one announcement. Just now we have posted one Google link in the chat box. So this is for just a general feedback form. So we will be really happy if all the participants can fill up the form and send it to us. And now I'm announcing the lunch break. We will once again meet at 2 for the post-lunch session. So enjoy your lunch and come back. We will meet you again in the post-lunch session. Thank you. Thank you all.
Good afternoon, sir.
Good afternoon. Can you,
sir.
good afternoon. Can you hear me?
Yes, sir.
Okay, thank you.
Sir, we will wait for a few more minutes, 4-5 minutes, and then we will start at 2.
Okay, okay, no problem.
স্যার একবার প্রেজেন্টেশনটা একটু শেয়ার করবেন?
Yes.
একবার একটু শেয়ার, হ্যাঁ।
Can you see it?
Yes, sir. Yes, sir.
So I am changing now. Okay. So is it visible now?
Yes, sir. Is it visible?
Okay, 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 fine. Thank you.
Okay.
So shall I check the slide show in the mode? So now can you see it?
Yes, sir. Yes, sir.
Is it in bigger font like?
Yes, sir.
Yes.
Okay, 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 okay. Thank you.
Okay, sir.
So I'll keep it here in this format.
Yes, sir.
So once you
Good
tell me, then I
afternoon.
can start.
Good afternoon, Professor Jana. This is Bimal Kumar Sarkar.
Okay, thank you, thank you.
It's very nice and also good for us that you have
Yes.
blessed us.
Okay.
Good afternoon, sir. Purva here.
Okay, thank you.
Shatarupa, can you hear me?
Yes, I can hear.
Okay, then after when the session starts, you can also start the recording. Huh?
Yeah, sure. In fact, I think the recording is on because the symbol is
not
showing.
not the live session. Separate recording in the cloud.
Recording is also on.
Okay.
Sir, since the students are still joining, so can we wait for 2-3 more minutes?
Yes, no problem. Please.
Okay, thank you, sir. Can we start now?
I think it's time. We should start.
Okay. So, good afternoon, all of you, and welcome back to the invited lecture sessions of National Conference on Frontiers of Modern Physics. I hope you had a good lunch because we have a lot of things in our schedule from invited talk followed by the parallel sessions. So it will be a long session. And before lunch, we had three very enlightening and thought-provoking lectures from Professor Amitabh Roy Choudhury, Professor Arup Kumar Roy Choudhury, and Professor Barnali Ghosh. I think all of you have enjoyed a lot. And like all the previous sessions, in this session also, we are delighted to have with us Professor Debnarayan Jana, a senior professor of Calcutta University. And this session will be chaired by Dr. Saurabh Kumar Neogi. So, Dr. Saurabh Kumar Neogi is an assistant professor of Department of Physics since 2016. He received his PhD degree from Calcutta University. He joined Indian Association for Cultivation of Science as a postdoctoral research after that in the Department of Material Science. His research work is based on synthesis and characterization of transition metal doped zinc oxide, commonly known to us as dilute magnetic semiconductors, and the field of half metallic magnetism. So with that, I would request Dr. Saurabh Kumar Neogi to take over the session.
Thank you, Dr. Vishwas. I am audible now?
Yes, you are audible.
So can we start, or
yes,
can we wait for 2 minutes more?
I think we can start.
Yeah, you have already started. Let people join and please start. Sir is also waiting for almost 10 to 15 minutes, so let's start.
Okay, sir. Hello, sir. DJ sir, can I start now?
I think sir got disconnected.
Okay, okay.
He has joined back again. Yes. Sir, can you hear us?
Yes, I can hear.
Okay. So, Dr. Neogi, if you can start the session.
Okay. Sir, can I start now?
Yes, please. Yes.
Okay, so it is really an honor for me that I am going to introduce my teacher, Professor Debnarayan Jana from Calcutta University in this session. Let me introduce him. Dr. Debnarayan Jana did his MSc from Calcutta University and PhD from Raman Research Institute, Bangalore. At present, he is a professor from in the Department of Physics, Calcutta University since 2012. He was a visiting fellow at NTU Taiwan during the year 2003-04, and his current area of research is mainly focused on zinc oxide, defect characterization of zinc oxide, ion beam irradiation effect on zinc oxide. In addition, he is also doing research in density functional theory on 2D materials and photocatalytic activities in different dyes. He has elected as a fellow of West Bengal Academy of Science and Technology in the year 2015, and he was awarded Distinguished Scientist in Physics by Venus International Research Award in the year 2017. Dr. Jana is known for his talks and popularization of science educations in his career or throughout his career. He has published almost 160 papers in international journals, peer-reviewed journals, and he had already written 4 review articles. I must mention one of his famous review article, which is published in 2009, Progress in Material Science, and I am also taking so much help from this review article. Almost 12 students have been obtained PhD degree under his supervision, and also 8 to 10 students are working at present for pursuing their PhD work under his supervision. And at present, he is a life member of Indian Physical Society and also editorial member of Indian Journal of Physics since 2003-04. and he received INSA Teachers Award in the year 2020. So with this, I request my professor to please start his talk, and if I do some mistake, please ignore this, sir.
Okay, thank you, Dr. Sarup. And I can see many faces of my students also in the audience, which I cannot see it. So let me be honored. At least I am being invited to talk about a recent topic of my research, and it's a really pleasure to present this wonderful audience for Adamas University, and I feel really honored to be invited for this particular lecture, because in this pandemic situation, it is very difficult for us to continue our research thrive to our students and the research scholars. But I must congratulate the authority and the other dignitaries for arranging such a conference and a discussion meeting so that the students can benefit. So I will talk today about the emergence of Dirac materials in the carbon family, which I'm doing research for last 4 to 5 years with students and the other research collaborators. And here is a list of few of my collaborators and which I'm working on the present topic. The research area of interest, as already Dr. Niyogi has mentioned, but mostly I am now concentrating on 2D materials apart from the usual graphene, and we have been able to actually innovated 2D materials by doing some theoretical calculations, and hopefully in near future, if things working properly, researcher can find out some of the synthesis route. So I have been working this problem with many of my colleagues, also from the college, like from Haldia Government College, Niladri Shekhar Mondal, then also our Anindo Sarkar from Bangabasi Morning College, then Suman Chaudhary, who was my student, now is also in IISc at RA positions. He's also been helpful for carrying out the researches. And Dr. Subhadev Nath from Krishnagar College has been also very instrumental in carrying out the researches in this area. So I have been thinking of telling little bit in the first half because there's so many students are there. So I will at least work it out one of the simplest system, that is the graphene, and then I will go to what we are doing in the last couple of years. So in the process, we will try to give you a theme for analytical calculation as well as some numerical calculations, and hopefully at the end I'll be able to transfer some messages for carrying out further research in this area. So my plan is the following. I will give a very brief introduction to Dirac material. Then, of course, we will present some kind of tight bending calculations of single layer graphene, which is doable. And we really teach this thing in MSc classes. That's a very challenging job that we can directly directly bring out the essence of the current research to the blackboard. And also we have been able to do some electronic properties of S-graphene and Fra-graphene, which were already proposed, but we have analyzed in a different tune. And I will try to share some of my works in that particular area, our group work. And then the last two things are that we will have proposed some new material of 8-16-4 graphines, which can be understood on the basis of DFT and tight bending calculations, and some more also new materials in the carbon family we have recently proposed, and we are working on it also. So I will also share my recent work on this thing. So let me start the journey, the way. So there is a conversation between two Nobel laureates, Professor Niels Bohr and Professor Paul Dirac. So Niels Bohr asked the question, so what are you working on, Mr. Dirac? So Professor Dirac answered that I am trying to take the square root of something. So what is something? Something looks like this. So he was trying to take the square root of px square plus py square plus m square without taking the square root. How can you write down that thing? And that gives rise to a wonderful solutions which Dirac can show that it can write down in the linear combination of Pauli spin matrix, that is px sigma x plus py sigma y plus m sigma z. So this was the two-dimensional versions of Dirac matrix. Actually, it was 4 cross 4 matrix. So I am not going to the details, but we'll take about this Dirac linear dispersion relations in our further discussions. So let me now go back to little bit basic physics of graphite. So it's a 3D allotrope of carbon, most commonly found in pencil tips, which all of us know. And this is a most stable form of carbon, but they have weaker interplanar coupling, so that van der Waals interaction is acting on that thing. They have also anisotropic properties like good propagation of phonons and electrons in plane, so along c-axis, and graphene, which have been formed, which basically is a single layer of this graphite, and it was a challenge for a physicist as well for the material scientist how to isolate this single layer of atoms. And it was the duty of Novosibirov and Kim, which I'll talk about later on. They use a specific techniques called the Scotch tape technique, so which can so that you can eliminate these graphene films from the graphite layer. So their multi-layer graphene, how does it show under ordinary microscope? It has been seen in the first slide, and under AFM, which is the most important characteristic tool to see this nanostructure, which have been shown in the figure 7, figure C, and the scanning electron microscope of a typical image of an experimental shown up as a D. So let me just read out one of the interesting lines from that paper. And as a historical note, that this paper was twice rejected from Nature. I repeat again, this paper was twice rejected from Nature. So it was finally the science editor. Thanks to science editors for showing us this wonderful experiment. Let me quote some few lines from their paper. Our graphene films were prepared by mechanical exfoliation, repeated peeling of small meshes of highly oriented pyrolytic graphite. This approach was found to be highly reliable, allowed us to prepare these graphene films, LG films, up to 10 micrometer in size. So it was a very wonderful technique, and you can get a good quality of film with almost uniform thickness, and stability criteria is already satisfied. So this is a pictorial demonstrations of many carbon families, especially graphene and graphite. These are the hexagonal structure of this thing. Remember, we have to choose a non-Bravais lattice like this thing at a rhombus. I will come back to this thing later on. And this shows semi-metal characteristics behavior. So these are the points known as Dirac points, where we can see the band level cross each other, and the dispersion relation is linear in P. So what is the basic difference between these metal, insulator, semiconductor, and so-called we are now trying to tell as a semi-metal? This is again a textbook material from solid state physics course. So we have plot E versus Px and Py and Pz. These are called the band dispersion relation. So this is for metal and insulator. There is a gap between valence band and the conduction band, and semiconductor there is also gap, but the magnitude of the gap is significantly smaller compared to insulator, and semi-metal when it just touches that valence band and conduction band. Okay. And this can be also visualized in another plot of using more transparent way in energy versus crystal momentum. because these are pseudo momentum. We know already that the block wave function is not the eigenfunction of momentum operator. So that's the reason we have to plot it like not like the usual momentum what we found out in our typical dispersal relation. This is called the crystal momentum. So metal has this a wide range of kind of where these electron hole excitations can take place. In the Dirac material, on the other hand, the valence band and conduction band touch at a single point. So the particle and hole excitation can very significant area. So that's very low significant area. So that's very important. You can control it properly if you have a small band gap opening here. And in the normal case of insulator, there is already this gap, which I have already discussed to you. And if you look out in terms of density of states, which is another useful quantity in condensed matter physics. So we know that this metal has a partial field band and the finite density of states at the Fermi energy. So G of EF, that is called the density of states at the Fermi energy, is not equal to 0. On the other hand, for example, semiconductor, we have a field band and that there is a gap at this level, and this gap is of significant value. We can calculate this gap or experimentally observe this gap by the two ways. One is by the electrical ways, another is by the optical means. But most of the band gap which is experimentally calculated is by the optical means, and there are direct band gap, indirect band gap. We are not going to the details of all these things. But graphene, which is a critical state, we can call it as a zero gap semiconductor, where this density of states actually zero or at a single point, or a zero DOS metal, whichever you can call it. That's the, since it's zero DOS metal, we call it just semi metal. That's the terminology used in the literature. So what so beautiful features in case of 2D material in general, because we'll use this thing many times. So it's a tunability, flexibility, that is bendability, and transparency. So we can actually call this as a all surface, because the interface between the surface and the substrate and the presence of these add atoms and defects can dramatically alter the material properties. And because of 2D materials, this property can be tuned using electrostatic or magnetostatic field. And most often the lattice strain also plays an important key role in modifying the lattice constant, and modification of lattice constant can give rise to the modification of energy bands, and as a result, strain engineering. That's very important. Strain engineering has become an emerging field to control the electronic and optical properties of all these particular material. So there are some difference between 2D ordinary and Dirac materials. Here I have listed for all of you, and this ordinary 2D materials obey 2D Schrodinger equation, but 2D Dirac material by its name Dirac equation, the errant momentum dispersion relation is quadratic, but in case of Dirac material, this is a linear. And here is this the energy level dependence in case of the magnetic field, that is proportional to N and proportional to B. Here it is not proportional to N, that is square root of mod N, and proportional to square root of B. Here the energy, 0 point energy half H cross omega C, but here this energy is 0. All these kind of differences makes it very subtle with the particular material. So hello, can you hear me? Is there any problem?
No, sir, no problem.
Okay, thank you. So there are also subtle difference between Schrodinger fermions and ultra-relativistic Dirac particles and massless Dirac fermions. So here I have again shown you a comparison of all these things in a pictorial presentation. So Schrodinger fermions means this dispersion relation, the Hamiltonian is quadratic. If you have a ultra-relativistic Dirac particles, then the dispersion is P, but the speed is C. That is called ultra-relativistic, because no particles in our existent observable world can have speed greater than the speed of light. So that's why the maximum speed. But in case of our massless Dirac fermions, we have this Fermi velocity. That's the only characteristic energy scales available particular kind of system, right? So these are the basic differences of these Schrodinger fermions and ultra-relativistic Dirac particles and massless Dirac fermions. So Dirac fermi materials, here is the basic definitions, because I'm going through the basic things because there are so many students, so they can actually capture this basic physics. So Dirac materials are a class of complex and functional nanomaterials which can offer greater potential in the development of new electrical component, electronic component, and there are few interesting points, so-called Dirac points, where these two bands cross each other. We can control the dynamics as well as the conductivity of the material through this particular point. So that's the important, and also there is a surface called the Fermi surface, which generally characterizes the material's property of a metal. But here, as I have telling you many times, the Dirac material, the surface has been shrunk to a single point. So the phase space is quite small. So normal metal. So what are the characteristic features of Dirac metal? So normal metals like gold and silver, they are good conductors of electricity. And the key aspect of this is basically from the energy depends on how does it depends on the momentum. As I have told you, the Dirac materials differ from the normal materials because the energy depends linearly on the momentum. Whereas in case of your normal metals, that is quadratic dependence, and within a material, the charge carriers such as electrons, which can acquire an effective mass, that's quite completely different from the bare mass. Because I'll show you in a few minutes that how can you calculate the dispersion from the dispersion relation, the effective mass of an electron, because linear dispersion relations. So how can you calculate? That's very interesting. So the effective mass and the number of states available for the electron to occupy when it is excited by an electric field, that actually is very important to for the device applications and other kind of particular transport features. So with these things, here is a comparison between the graphene as a versus bulk semiconductor such as silicon, gallium arsenide, indium arsenide, indium, gallium arsenide, which are very commonly used. And I'm not going to the details of all these numbers, but at least I will try to show you that the band gap of silicon is 1.12. This is gallium arsenide is 1.42 eV. Then this indium gallium 0.72, 0.36, 0.18, and this is completely zero. That's very important. And if you calculate the ballistic mean free path, which is very important, so this is quite large, that is 400 nanometer, because this much distance can electron travel before it is scattered out. So that's very important. So people are trying to have already done that particular thing in the device, like FET transport and FET measurement, current IV characteristics, and other things are there. So it has also very high mechanical strength, and this is the strongest material in the world. Zero band gap, I have already told you, the highest mobilities of any material, twice the diamond highest thermal conductivity, and so on. And one of these region of these extraordinary properties associated with the graphene is because of the following fact: we can almost synthesize this graphene almost defect free. At least there is a small area in the graphene sheet where there is no defect. This is not possible for any other 2D materials where defects naturally occurs ubiquitously in nature. So what are the basic aspects of graphene? How do you construct this graphene in computer? So we know that these carbon atoms in graphene are sp2 hybridized. Two nearest neighbor carbon atoms from the unit cell of graphene. The typical bond length in graphene is 1.42 angstrom, and the two primitive basis vectors which I have chosen here, A1 and A2, they are given by this particular thing. And Brillouin zone is hexagonal with the three most symmetric, that is the most symmetric point is the gamma, that is Kx, Ky, Kz are 0, and electronic band structure around this point K, they are actually linear, that are the Dirac point. So with this thing, I just go to the tight bending calculations very quickly because this is available. So once you get this A1, A2, we can calculate tau1, tau2, and this the translational vector, which is a two-dimensional hexagonal, and we can calculate the reciprocal lattice vector. Remember this lattice vector which I have chosen, A1, A2, they are not orthogonal. So that's not a Bravais lattice. So once you get that thing, then you can define all your below zone points, gamma, m, and k by these things. So everything is satisfied by this bi dot aj is equal to 2 pi delta ij, which is the basis of calculating the reciprocal lattice vectors of any particular two-dimensional case. So how can you calculate this graphene tight bending calculations? We have to calculate the matrix element via this kind of algebra. And once you calculate this 2 cross 2 matrix element, H11, H12, H22, and H21, you can calculate this dispersion relations. So here is this H12 calculation, which I have shown it here. T is the hopping parameter of nearest neighbor interactions. So once you get that thing, you can calculate the finally the dispersion relations, diagonalizing this matrix, and you get this plot of this K and K dash. So there are 6 points in this thing where these two bands crosses each other, and we can get this Dirac cones along that thing. So I have already told you 2 bands touch each other at 6 points. 2 of these point K, K dash are inequivalent. Rest are related by transitional of this lattice vector, and around this point, as I have told you, that Ek can be written as plus minus Bf of mod of K. So rather than 2 equivalent Fermi points rather than a Fermi lines, and Dirac cone about the K and K dash point. So these are the features of this band dispersion relations. Now, how do you show that this Ek around this Dirac point is linear? So here is algebra. This is called the low energy analysis of this in the long wavelength limit. So you read small k equal to capital K plus Q, Q is small, and we expand this e to the power ik dot A1 as this following way. And once you get that thing, you can determine this Fermi velocity in terms of the lattice constant and hopping parameters, and you can calculate this Fermi velocity. This person is indeed linear, and we can write down this Dirac matrices and Dirac way of writing that thing, which I have told you, Dirac like Hamiltonian in the beginning. This is the form of this Vf, that is the Fermi velocity, and this is the linear. So the dispersion relation is a linear in P, that is linear in momentum. So this completes the analysis that showing that the low energy physics in graphene is completely controlled by the Dirac like Hamiltonian in 2 dimensions. Only a difference is that this is massless because we have linear in P, and in case of ultra relativistic particle, normal Dirac particles, that was the velocity was speed of light, but here it is taken the Fermi velocity, and in particular this Fermi velocity Vf is C by 300, roughly speaking. So this is again the features of this particular thing, summarizing all this density of states Brillouin zone and the Ek diagram. So this is simple. So now, as I have told you how to calculate effective masses at the Dirac points. So here is this relation. This is again a standard textbook type of thing. We know that effective mass inverse is related to the curvature of this energy band dispersion, that is 1 upon h cross square del 2e del k square, and you have this dispersion. So you have to do this calculation. It is just like a 2 cross 2 matrix, and if you do that thing, the trace of m theta, it turns out to be 1, and determine m theta is equal to 0. So that's why this m star minus 1 at this point is 1 is 0 and 1. So the effective mass is 1 point it is finite, another point it is actually this infinity. So that's the difference between the effective mass of the Dirac points, and this is the way one can calculate this thing. Okay. So that completely solves this problem of this Dirac point, how to calculate this effective mass of electrons, and that's very easiest, and we do it in the classroom teaching. So that's why I show and share this thing with you. And how can you see this really forming this Dirac point? Here is this famous example, famous experiment called the ARPES data, that is called angle resolved photo emission spectroscopy data. And you can easily visualize that these Dirac points are actually meeting each other, and there is a small gap in particular area if you go on very keen in, but this features is already illustrated by this ARPES data. So question is that is graphene the only material which having Dirac cones? Answer is no. There are plethora of many 2D materials which have been discovered in last 10 to 12 years, different materials with either single element or some two elements or the compounds or the nanodimers and etc. So people are searching for these various materials having Dirac cones. And why these Dirac materials are rare? There is a very nice argument given by Professor Wang in Natural Science Review in 2015. So he mentioned that if there are three hopping integrals where T1, T2, T3 are the nearest neighbor, next nearest neighbor, next nearest neighbor integral, then they must satisfy something like a triangle formation, which is given by T2 minus T1 must be less than equal to the T3 magnitude and less than equal to T2 plus T1. And if there are 2D materials having two atoms of same species in each unit cell, then there is another further kind of restriction on the hopping parameter, and the interested readers are being requested to read this article more clearly for many interesting discussion on that thing. And there are criteria for existence of Dirac cones coming from symmetry and parameters and Fermi level and band gap. So you have to respect the symmetry. Otherwise, you cannot reduce the number of equations to be solved. And sometimes what happens, the proper parameters are required for the existence of the solution in real space, real values of kx, ky. So sometimes it happens that ekx, ky, you may not get the real values of kx, ky to cut that point. So that's why your Dirac cones are absent, that thing. So there's a very nice argument which was given later on, and why these Dirac cones appear. So that can be understood by 2 cross 2 matrix, what we do in the case of typical degenerate perturbation theory. So HK can be written that H11K minus E and H12K, H21K, H22K minus E. So write down the secular equations and you will find out the degeneracy of the two roots are equal, tells us that H11K should be equal to H22K and H12K should be equal to H21K equal to 0. So in most cases, what happened, the space-time inversion symmetry tells us the first condition is well satisfied. But the 2D system symmetries cannot guarantee that you can have an existence of that thing. So because what happens, the number of variables, that is 2kx y, usually less than the number of equations which determine the Dirac point. So that's the precise reason that not all of them which are promising to be, or the researchers are finding that Dirac cones to be found out, but that cannot be found out. So two conditions have to be satisfied clearly, that is H11K must be equal to H22K and H12K equal to H21K equal to 0. So there are many design of carbon allotropes from CC bond of graphene, and there is a list of all these things. I have shown you graphenyline, pentagraphene, twin graphene, 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 biphenyl and H18 carbon. And it is very interesting. Last couple of, I think 2019 onwards, biphenyl ring has been synthesized. That's very amazing that it has been synthesized, and lots of work is going on this biphenyl ring. And there are also design of carbon electron from a CC bond of graphene. So here is also a list of all these things, but it turns out that most of them are actually the metallic in character. Okay, so there is no kind of any possibility of some kind of Dirac cone or something like that. And there is also classification of 2D carbon allotrope via this thing like 4, 6, 12. graphenyl 4, 6, 12 ring. So it is, I'm talking about 4 is tetragonal, then 6 hexagonal, and 12 is the other more than this is that is the ring which we are considering. That 5, 6 ring, penta means 5, hepta means 7 ring. Like this way, this nomenclature are given like that thing. One interesting aspect from this table is that there is no mutual, there is exclusion of tetragon and pentagon in the existing structure of 2D carbon allotropes. So what we try to do this analysis via 2 methods. I have shown one at least tight bending method, and another very popular method is the density function theory. And I'm not going to the details of this density function theory, but at least telling you the in Schrodinger view, that was the wave function. DFT, it was the density. Density is a function of real function of 3 variables, and this problem can be solved in even in a laptop or a computer rather than the wave function approach. And for this thing, Nobel Prize was given in chemistry to Professor Walter Kohn. And here is a self-consistent scheme which is used in DFT. You start with energy functional. Again, it talks about only the ground state electron density. There are many terms associated with, especially this exchange correlation term is the very important, and your whole of this understanding of the physics is boils down to how to check or how to change this exchange correlation function suitable for your problem. That's the hard part of this particular DFT calculation, but other things are quite easy. One can do even in a laptop. So you start with a trial density, and then you go on doing this self-consistent calculation till you get a optimized ground state electron density. And here I'm showing you a cartoon picture directly taken from the Nobel laureate website, that is band structure of graphene nanoribbon. And you can check that once you add the different width of this particular nanoribbon, the band structure sometimes become graphene like a metal, sometimes like an insulator, sometimes like a semiconductor or semi-metal, like that thing. So this is very interesting that depending upon the width and the size and the morphology, graphene nanoribbon could be semiconductor, insulator, and whatnot. So let us start our journey now into this world of this Dirac material. So we have now given till date the work actually associated to how to go to the Dirac system. Now we are presenting our group's activity, our groups in last couple of years. So here is a model calculations, very simple problem in the graphene network. If you substitute the boron and nitrogen, what happens to these particular things? So here there are 2 equivalent and there are non-inequivalent points or non-equivalent points. So here C1, D1, E1, these are non-equivalent points. A, C, D, E, these are equivalent positions. And there is a, if you dope this thing, there is a possibility of changing the electronics band structure. And here it shows that if you do this calculation, this band structure, it turns out that nitrogen dope and boron dope, and if you do nitrogen boron co-dope, the band gap actually changes with the doping concentrations. That's very wonderful, and it is nice to share with you that this was experimentally done after 4 years of this work, and that was also published in Carbon, one of the reputed journal in Elsevier for this material scientist community. And so what we have predicted, it was verified there. And there is a nice experiment also later on, which also confirmed the yields, which was shown by this the red line is basically the DFT calculation, and the experiment was coming by these circles. So you see a almost quite nice match with that thing. Not all these things are there because there are so many approximations involved in this DFT. However, at least 2 things are important. There is Yeltsin peak at 5 eV series, that's very important here, and around 15 eV. This is now confirmed, and any experiment involving graphene, this thing is quite important, and till date there is no violation of this thing. So that's why I think this work is quite cited now. And we now move on to another graphene system called the ACE graphene, which was actually proposed in Zhu et al. And 2014, it was predicted from the structure searching method Calypso. There's a very well-known code where you can actually search, optimize, and check it. And then first principle calculation was done in vast DFT calculation. This is also very popular in DFT community, and it was found there are 2 points where these Dirac points can emerge. So 2 Dirac points here independent of the other things. The question we ask the following thing, that why does this 2 Dirac cones there, and can we control the Dirac cone, like 1 Dirac cone and another opening, or 2 Dirac cones and another opening? What are the kind of features associated with that thing? So this work was published in scientific reports, and we use basically a real space renormalization group technique, that is RSRG group technique, to do this band dispersion relations, which is actually shown in this slide. And here we actually try to do an approximation near this Fermi level, and we have this particular choice of this hopping parameter, which we have shown it by this particular side, that is T2 square mass satisfied T1 and T4, and T dash and T double dash, which after this decimation, which has come down like a very simple 2 one-dimensional chain, where we can do this approximation, where this scheme actually works there. And it turns out that this RSRG is basically turns out to be a 2-level system, which I have shown you here by doing many decimation process. And if you start with a uniform hopping in the original lattice, it will turn out in the Phyline lattice also uniform hopping. So these are the very well-known prescription, and here we show the comparison of this RSRG scheme, this existence of 2 Dirac points with this A and B point, and here is also from the DFT calculations, and the dispersion relation, analytical dispersion relations around these points have been shown it here with this QX, QY, like these particular values. And we can further control the Dirac point band gap opening by choosing that appropriate values of hopping parameter. And here are the conditions that where you can have this A Dirac cone present, but B Dirac cone opening band gap, and vice versa, and various other conditions. So that gives you to a wonderful understanding of analytical understanding along with the DFT input, that we can understand this robustness of this individual Dirac cone in this particular prescription. Also, there is some topological aspect associated with that thing, but I am not going to that details now because that will take more time. Also, we have done some other work on the graphines where this acetylene linkage and alpha graphene system has been there, and there is a recent experiments on synthesized of this particular graphene material in the nanoribbon form, and sheet also in some, not in the free form, but in the some substrate. So we hope that our result, which will have published recently in PCCP and other reputed journal, that band structure and other features, optical properties features can be obtained with this thing, triple bond linkage, and that can also be very quite fruitful for the experimentalist, and we hope that that particular material will be synthesized in near future. So here also we can see the Dirac cones and other things. And now I am now coming to this another important graphene system 8164, which has not the hexagonal but the square lattice topology, 2-dimensional, but instead of the Dirac cone we get a nodal line. So here is this particular material, and we have checked by the charge density, also the phonon mode, and also the atomistic molecular dynamics simulations, that this structure is quite stable even at 1000° K, and there is no negative phonon mode. So all these calculations, apart from the mechanical stability and optimization, tells us to go further, and we have seen from the DFT calculations that there are Dirac points, but not at that particular K point. There is other points. So we now use this RSRG scheme to show analytically that why are the two Dirac points. And here is this complete RSRG process on the original lattice of 8-16-4 graphene. And there is a class of other kind of materials which can also be used by this particular RSRG scheme. And here is this kind of matching with the DFT result and the existence of Dirac points, A and B point. Here is this graph of E versus Q curve, and this is the particular charge density plot at that particular point. And here there is the presence of nodal line rather than the Dirac point. So if you actually see this particular thing, you will find out this particular structure in this thing. So that's why I'll call it is nodal line. So here is also another interesting feature. Some Jack index can be also obtained. That is the topological feature associated with this particular material, and this can be calculated by 1R60 or some Berry's curvature. So we calculated from the edge states how to calculate this particular quantity. So we have found out there are regions of W equal to ±1 and 0. So this is related to edge states, and we can characterize these edge states by this something like Chern number, which is used in the quantum, used in the fractional quantum Hall effect by the topological index number. So there are restrictions where this Chern number is 0. There is restriction whether the Chern number is integer positive and negative value. So we show a phase diagram associated with this particular point where we define P1 and P2 via this particular module of 2, and we found out the existence of this thing apart from this colored region. So all other points this are is not very significant. They are not topologically equivalent. So this is another exercise in this 2D material that we can actually predict some characteristic associated from the band structures only. So this is wonderful. And recently we have done another two-dimensional carbon system as a potential and lithium adsorbent. And although the system was not Dirac, but it's isostructural nitride form. So when you dope by this nitrogen, that shows Dirac fermions. And here we apply both the DFT as well as the right bending RSRG approach to do that thing. So here are the structures which have been formed, and this is the C is the phonon mode calculations. So there are structure possible, then we will have to calculate the phonon mode, whether it is positive or negative. And we have got these two structure, that is PHP graphene and metallic, that is 5444 ring system that does not show any Dirac form. But look at this particular point, which can give rise to some interesting features if you dope by the appropriate material. So we doped actually versus a nitrogen, which is shown by this particular ring, and there are two different positions of this nitrogen which you can find out this existence of Dirac cones. So here we show this Dirac cone feature in this particular E versus K curve, and this is the charge density plot. And that is also interesting to share with you that although the pristine sheet is not that much like two-dimensional Dirac fermions, but if you appropriate and look at the particular choosing the appropriate sites where to dope with the appropriate add atoms, that can give rise to an interesting Dirac fermion. So this is one of our last work, which can show that although the sheet is not having this particular Dirac fermionic properties, but the derivative material, appropriate site-dependent derivative material, that can show like this thing. So we also have shown another material, twin-T graphene, a new semiconducting 2D material, which we have also proposed, and their elastic constants have been there. There is a possibility this material might be synthesized, and few people are working on that thing, but we were the first one which we proposed this twin-2 graphene. So this is the tetragonal graphene, T graphene in tetragonal graphene, which we have shown in the structures, and we have this the charge density plot. And this is also very interesting that this has a semiconducting 2D carbon electrode that can be used for many device applications. Apart from this thing, we have recently also worked on in Dirac cones in far graphene with site-specific doping, and this has been accepted, and it is due to appear in applied surface science. And here also we use the same thing which we understand in the last work. There is the site-dependent doping which can give rise to this particular opening of band gap or not. That opening of band gap actually in the Dirac material, which I have told earlier, if you add foreign atoms, that there will be a gap opening. There is a very simple way to understand this thing, because when you dope, let's say in the hexagonal graphene lattice, if you dope boron and nitrogen, then it will be hexagonal boron nitrogen alternatively. But we know that hexagonal boron nitrogen has a large band gap. So why there is a band gap? Same structure, only two different add atoms can give rise to this band gap. The simplest way to that thing, it changes the sublattice symmetry. So the environment changes, the carbon environment changes, the boron nitrogen, that environment changes, the charge distribution changes, and as a result, we can show that by just 2 × 2 Hamiltonian, because of the sublattice symmetry breaking, there is a opening of band gap. So here also we actually adopt that particular technique to show that how can you open a band gap or not, depending upon this particular nature. And we use also the tight bending RSRG approach to do this analytical calculation. So both powered by DFT and analytical calculation, we have been able to show that Dirac cone from these hopping parameters, and that gives you a nice relation, a very simple relation between the hopping parameters, and which actually that analytical calculation completely agrees with our numerical calculations from the DFT. For example, the Fermi velocity and other kind of material, other kind of proper parameters for particularly this particular far graphene can actually give rise to wonderful experimentally verified quantity. So we hope that this particular material also may be synthesized in near future. The far graphene nanoribbons have been synthesized, but this work is based on seed. So we hopefully think that if this work is synthesized, then it will be nice to check our predictions. And there is a wonderful topical review which we have been published just now, 1 week back. So any interested readers can go through this thing. There are many materials which have been summarized here and predicted also there, and which have been synthesized, which have not been synthesized. All these categorically have been given. And also there is a wonderful way of how to do these calculations, even in a laptop or in a kind of a desktop, that some hints have been given. And I hope the readers can be benefited from reading this, lucidly reading this article. And with these things, let me conclude here that Dirac materials are to be transparent to light of a given frequency of polarizations. When there is a particular polarization, light is incident on it. This material would be opaque to the same light when it falls it from a different direction. There are many different applications for transparent conducting films. The common example is touch screen in mobile, which we are using here. So hopefully graphene can break way it can change it, or other 2D materials can change it. Optical conductivity is an appropriate measure of this opacity offered by the material to the passage of light. And we hope that this high optical conductivity of semi-direct materials for this particular electromagnetic waves will give a new direction to the device applications. And there are many other basic approaches which I have trying to illustrate that analytical dispersion, relation, robustness of this, robustness of the Dirac cones under strain or under electric field. All this kind of problem can be calculated. And also these topological aspects, which are another interesting aspect of particular these materials, which also could be an topic of big science research. So with this thing, let me conclude here, and I'll be waiting for comments and suggestions. And here are some few papers from our group, which have been used to for this particular talk. And I'm sorry that I do not cover all of my research here, but at least if anybody is interested, I'll be happy to discuss with him in my lab or with my students and other collaborators. And hope these are my group members. So some of these people have already submitted thesis and waiting for their thesis report, and one more have joined also. One more students have joined in our group recently. So hope in near future we'll be able to contribute something to the material science. And with this thing, I'll conclude here. Again, once again, thank you all for this arranging this particular talk in this particular regime. And I think in this year, this is the first talk I am giving to this university. So hopefully I'll be happy to help you in any other matter which you think is possible from my point of view. And again, once again, thank you. Thank you for your kind attention.
Thank you, sir. Thank you for your very nice talk and very informative talk. And I just want to ask one question, sir. In one of your recent publication, you have considered the 20 graphene.
20 graphene, right? Tetragonal graphene, yes.
It is possible that it can be synthesized. So, is it possible by simple technique we can prepare it?
No, it is not possible till now.
Okay.
So people are trying, but lots of theoretical and propositions are going on. So this, I think, model was, I think, 2019 we first proposed. And we had a very nice chat with Professor Arup Rai Choudhury and S.K. Rai in a conference about the possibility of synthesis. But till now, there is no route found out. But it has a very good potential candidate. People have looked at it. That's why this paper is now quite cited.
Okay, sir. So anyway, sir, it is very informative and very useful for us that really we have get a lot of information regarding at present in which direction condensed matter physics research is going on. And as I have discussed with you already earlier, that in near future, we will try to request you to please come to our department, and we will arrange some workshop. And in this workshop, if you can give some idea about DFT calculations in this.
Yes,
different
no problem.
system.
I'll be happy to do that thing. Because most of the codes are 80%, I think, software and codes are available. So if you can choose appropriate codes for the machines and other things, some work can be done. I think I can. And that's why there are some colleagues from different colleges, I said in the beginning. So I am very happy they have come forward to work with me. And we have been able to build up a good group from last couple of years. So that's why we can do a good work.
Sir,
that's a very wonderful.
Sir, this is Vimal Kumar Sarkar. Actually,
yes, please.
Both of code, the DFT code in the Win2K and VAST are used. Sir, for 2D material, which code is better, sir?
That's a very good question. Actually, first of all, we use basically because VAST actually takes some more time, but it is very good indeed. And it is you cannot get free. Both VASP and ATK are not free. Okay, yes, so we use basically quantum espresso and siesta. And for other kind of thing, for minimizations like Phonon or Phonopy, these are done in some specific group. So they actually do it very fast because we cannot do it. So what we do is the band structure and the optical properties calculation are done by us. Other part, actually, we take help of some other scientists and few of my students, earlier students and colleagues. So they actually do that part. So analytical and other part are there. But I'll tell you, each of these software are designed such a way that they can do that part very efficiently. For example, ATK, they can do the specifically device application. For example, IV characteristics. So you have a seat and you have taken as a gold plated and you want to calculate whether it could be a diode or a time diode, like this thing, IV characteristic. That is very nicely done in ATK, but that cannot be done in other software very efficiently. You have to write some code for it. And we have actually written a code for that. So we do not, because we do not have ATK here. Although our university has ATK, but there is a problem in Nano Center. We cannot, and nowadays we cannot use it. I think I remember once I have done this thing, but I cannot extract any data. And VASP is the best one, but it needs one person to learn thing. It takes time, 6 months, it takes time. The new learner should take, but Espresso and Siesta, I think within 2 months, he or she can learn it. There is no problem.
And sir, another problem also, just when we go for phonon calculations,
right?
Then sometime Phonopi or Phonon, these softwares are used.
Yes.
But the problem is that when we go for the calculation Phonon properties using Phonon, there is some
mismatch.
Mismatch.
Right.
This is
I know. Right. Very good questions. Actually, we also face the same thing. We could not do this thing, but nowadays I can tell you one wonderful things have come, and we are trying to learn, and we have done the machine learning language. I think you should adopt this machine learning language, and there are many few courses are going on. So if you can learn that thing, it will be nice.
It's a very nice suggestion, because nowadays machine learning is being implemented in many places.
Actually, one of my group member is expert on that thing. He ran that program in actually in Russia. So he was a postdoc there. So we are very fortunate to that.
Okay.
Otherwise, we have published some 2 papers on machine learning language. I think that was the only paper from Calcutta, I think, using machine learning language. Nobody is using machine learning language. But I hope within next 3-4 years, everybody have to use this machine learning language in any form.
Okay, so good suggestion. Actually, also we are in the process to establish one material science research center. And there one group is will be doing work on theoretical aspect also to support the experimental result.
Yes.
And sir, your nice suggestion will be taken over also. Because in that case, machine learning can be taught also.
Yes, and almost 80% softwares are free of cost. Machine learning language. We are actually trying to grab all these softwares and trying to install in one computer so that we can do that thing. So that's we are in the process. So hopefully in the next year we can, one of my students can start doing that. So that's my plan.
Thank you so much, sir, for your very good suggestion. Thank you.
May I ask something?
Yes,
sorry?
please. Momita, please.
Sir, how are you?
Fine.
It looks that you took us 15 years back. I felt that I am in the classroom till now.
Yes.
Yes.
Nice.
So, sir, I do theoretical research a little bit. So I wanted to know, sir, you talked about graphene. So does graphene have the same, I mean, I don't know about it. So does graphene have the same structure like 6 Dirac points and all that?
Not all of this thing. Graphene has various forms. Some of them have Dirac point, some of them, because graphene, there is double bond. Here there is triple bond. So there is some problem.
And
not
sir,
all of them.
Okay. And sir, we know that we observe some sort of age states in zigzag graphene nanoribbon, but not in armchair. So if we talk about graphene nanoribbons like that, so does we observe age states, because age state might correspond to localized state which contribute to electrical current. So if the Fermi energy lies in that region, it will act as an insulator. So that is why I just wanted to know. Does
it has been done? Yes, absolutely. It has been done. And because of this age state, magnetic property also can be controlled, as you can see that.
Okay.
So this has been done already.
Okay. Thank you, sir.
Actually, that was one of my students' thesis work. She is going to submit, Susmita Jana.
Okay, so she has worked on graphite.
Yes, yes. So actually the last review articles in JPCM, which I showed you. So
yes,
everything has been
2D
listed
materials.
There. Yes,
the
yes.
topical review. Okay,
Yes,
I'm planning to read that very soon.
Okay, okay. So
okay, sir.
Okay, actually,
and sir, it would be our pleasure because now we are almost taking all offline classes. So it would be very good for us if you visit our lab and our department one day.
Sure. I have already talked with.
Pleasure that we are inviting our teachers to our own job place.
Sure.
Please come.
Yes.
Whenever you can. Okay. Sir. Thank you.
So, any other questions from the
audience or
audience, students, and faculty members?
There is no question in the chat box, so I would request the participants, if you have any question, then you can write to us. We will forward those questions to sir, and maybe he will be able to answer.
Yes, I think there is no further question. So, sir, thank you very much for your very nice presentation. And it is really a good, very great pleasure for us that we have with you in this online mode. And in future, we are planning to conduct some seminar, which is in, of course, in university. And thank you for your presence and very nice presentation.
Okay, thank you. So I'm now leaving.
Thank you, sir.
Okay, thank you.
So thank you, Dr. Neogi, for chairing the session, and thank you, Professor Jana, for such an important topic that is discussed so lucidly and so explained so nicely. And we also had a very nice discussion session.
Thank you, sir.
Thank you.
And I think you got many students more than your normal classes in the university.
Okay, thank you.
As like this session means we are also student. Actually, Purva.
It's nice to see all of you in this after this pandemic situation.
After many years,
so maybe
going back to the class.
maybe in the next year we'll start one session for all our alumni session, so that we can arrange a reunion. So we are thinking of that. Let's see whether you can call all of you. Sorry.
Sure, sir.
Okay, thank you again. I'm leaving now.
Thank you.
Thank you, sir.
So with this, we have come to the end of the invited sessions for this conference. We had a small tea break, but we were supposed to start at 3:15, the parallel sessions. I think we can all join the respective sessions, parallel sessions. And there is also a feedback link given in this chat box here. So participants, you can feel free to give us the feedback. And also we have a valedictory session from 6. So I would also request the participants who will now get distributed to different parallel sessions to come back to the valedictory session, and we will end the conference there. So for now, let us leave this platform and go to the other sessions.
Thank you, Shweta. So we are joining the parallel sessions.
Yeah.
Joining there.
Okay. Recording needs to be stopped.
Yes.
So from this we can leave now.
So we are meeting. We are starting the parallel sessions sharp at 3:15.
Yeah, sure.
Okay.
So I'm leaving now.
Yeah, I'm also leaving.
And I'm joining the parallel session.
I'm also leaving and will join the parallel session.
Okay.
Very nice. Thank you. It's a very good session.
Okay.